Good morning, everyone. Woo! Okay, so we are slow comers this morning, but it's fine. We'll get there. So today is day 2 of FAB26. The theme of the day is tools and tech. And I would like to start with, well, we have a lobster coming up tomorrow, so just stay tuned for that one. That just changed. But things you need to know. So the weather, I'm going to start with announcements. And the weather is a little bit unpredictable this day, so just make sure you have your raincoat or an umbrella. That way you don't get wet and you don't get late onto your sessions. Just make sure of that. We do have a time travel website. If you are not familiar with this one, it's basically a light version of an Instagram, but just for all members of the community. So just scan the QR code and you'll be able to access and upload videos or photos of anything. It doesn't need to be related to the conference. It just needs to be related to Fab Labs in the community itself. So we are creating an archive of photos of the community to be displayed on Friday. So if you add your photos there, they will be displayed here on Friday. Thank you. Next, just to make sure that you're being photographed and video, we're live streaming this session, and it's live on our YouTube channel. Still, the transportation is down, especially for the red line, just between the areas we are at, wherever you need to go to wherever you need to be at. And there's a couple of shuttle buses that can also support this process. Same again, if you did not do that, we did have an overwhelming community basically getting into our app. We run into some issues, but we have solved them yet now, so we should be fine. Just make sure you're connected with our WhatsApp. Just so everybody knows in terms of activities, we do have scheduled activities, but there is no way sometimes for us to confirm if the presenter is coming to the session. Sometimes they don't notify us, sometimes they come late, sometimes they have a delay with their flight. So just be patient and get close to one of our team members, and they will be able to support you or guide you to the next session if that's possible. Also, there's changes on the fly, so just make sure that you refresh your schedule before you get to your session. Reminder of respectable spaces especially in E14 and E15 buildings at the Media Lab. Just make sure to don't disturb other spaces that are not allocated for FAB26. And we have something special. So everyone got a bag when they register. So that bag has a bunch of squares. That's like a bingo card. I don't know if you noticed that. And now we have a bunch of stickers that you can actually, well, it's not stickers. Well, I'm going to call them stickers that you can put in each of the bags. They represent all the different editions of the Fab Lab conference where you have been to. So if you were in Fab 3, or if you were in Fab 11, or if you were in Fab 13, you'll be able to add that and personalize your bag and let us know where you have been throughout the 22 editions of the Fab Lab conference. It's going to be located at the hub, right there where you see the Fab Lab logo. And just a reminder that everyone that we have lunch at E14, our building C in a map, and in the 6th floor. Just try to be there in time. We do have capacity for everyone, and hope you're enjoying lunch. Today, we're starting the sweets and snacks exchange that Claire has prepared for us. So if you brought candies to share with the community, this is the space for you to exchange them. It's also going to be in the 6th floor. And I don't know if you knew this, but every year we receive an overwhelming amount of talks. People love to talk. People love to talk. I would say this year we received around like 100 different talks that people wanted to submit for the conference, which is fantastic. And we want to hear you all, but you know the time is limited, and that's why we are starting this really on time, just to make sure that everyone has enough time to speak. So we have created a little section of some of those to be presented up on the main stage. We still have talks in the afternoons that you can all participate in. So the first Fab Blast of this morning is it's from Fab Lab designs to local production, Kenya biomaterials manufacturing of kinetic seats. And this is going to be presented by Koshi Kato. So with that, Koshi.
Is mic on? Thank you, Norella. I am an engineer in Toyota, and I joined Fab Lab community 2 years ago in Mexico. And I started Fab Academy program. Then I developed Fab Labable kinetic seat. Kinetic seat is a unique seat which I have been developing in Toyota, designed to utilize our spine function. It has 2 rotational axes, one on pelvis, the other on chest. Spine function stabilizes your head, especially on the bumpy road. Seeing terrible road conditions in farmers' field in Kenya, I was sure that my kinetic seat is going to help. I wanted to make our innovative seat accessible to farmers in Kenya as a made-in-Kenya product. As consistent as the Fab Lab way, I designed, then share the digital data for fabrication in any Fab Lab anywhere. The seat is actually improving your riding comfort a lot. Look at the chin. And the strong brake, the head dive never occurs. It was successful, but still need improvement. Lightweighting for performance improvement, especially for the moving part of the seat. Lower material cost by finding less expensive locally available natural materials, faster fabrication with components, and fabrication improvement. Our first version, the whole body parts were made out of plywood, which needs a CNC process, takes a long time. And discarded car seat belts were used for the seat fabrics. It took us 3 days to complete with 1 engineer and 2 technicians. For the faster fabrication, we minimized the plywood CNC part. For mass reduction and the material cost reduction, we chose bamboo strips with its strength. To assure the accuracy of the bamboo bending part, its hand bending part, we made the digitally designed molds. This is our processing. Steaming the bamboo. The material follows this digital data and bending with the clamps and putting the glue and clamps again and heat for drying. And this is the suspension system of the bamboo made by Sisal. This is assembly part of the moving part of the seat. And Sisal was made out of the plant, dyeing, weaving, and ready for the test. And we asked professional tuk-tuk drivers for the test drive.
But that seat is very, very much comfortable. You don't feel tired. You don't feel potholes. Mm-hmm. Yeah.
How do you feel with the Sisal and the previous thing that you used?
The Sisal one is soft. That one was very hard. You could not sit in that one for longer time.
They're going to order a lot of kinetic seat for Fab Lab Vietnam. And for the further business chance investigation, we did the test drive with the Safari Tour vehicle.
Because it's giving you One, a taste of nature. This car is a nature car. It's all about nature. The seats are natural. You get?
So our next steps are production process refinement for consistency and quality, safety tests, especially for the Safari Tour conversion vehicle. Pilot programming is going to start with Tuk-Tuk Association in Kisumu. If you are interested in this project, I'm going to talk detail tomorrow afternoon at museum. And also, together with Rico, we're going to organize the theoretical workshop discussing about the project for the Global South. Thank you very much.
And now we're going to continue with our next Fab Blast. From AI to a bronze sculpture, 3D printing as a way to make data concrete. And this is by Rico Bassi. Sorry.
Hello, everyone. What a pleasure to be here. So I want to tell you a story about technology that meets traditions, and that's the story of this sculpture. I'm an innovation consultant beside being a part of this community since 2011, and very often innovation happens between the gaps of what already exists. A big gap nowadays is created by AI, where digitally you can do basically whatever you want, but then when we want to bring that back in the physical world, sometimes that's not so easy. So the gap is actually the story of this sculpture called Atomic Reverberation. And Atomic Reverberation is a project by Mauro Martino. Mauro Martino is an AI and data artist. He's actually working around the corner because he's the founder and director of Visual AI Lab at IBM Research. So it's literally 15 minutes away from here. He's also a professor, started his PhD in Italy, and then he ended up here in MIT. So Mauro's been obsessed with the data visualizations, in particular data visualizations of very complex networks. So how do you explain the complexity in an appealing way? That's not an easy task. And in his own words, he wants to work on explaining how AI refers to itself in the different projects and paper and research paper that he did. And to do that, he represents every paper as a node in these very complex networks and let the AI he developed to describe the relations between the paper. So how much a paper referred to another one, a research referred to another one, and see what are the key nodes in these very complex systems of research that happens at IBM. He designed an algorithm that represents these connections, and every time you run the algorithm, that again is AI-based, you get a different results. And that's the nice thing. Every representation represents the same data, and yet you get diversity in there. He also made some of these networks as sculptures through 3D printing, of course. But that's an easy task somehow, no? You get a 3D file, you just press print, and you got it. But you have limitations, in particular on materials, for instance. So at a certain point, he decided to switch to a more complex but also beautiful material, such as bronze. And he contacted the artistic foundry, Battaglia, in Milan. This guy's been around for more than a century, and they made statues the size of like 3 buildings, 3-floor buildings, tons of bronze in that. And they are not afraid of complexity. I mean, they really worked with every important artist around the world. This is the list up to D, because I didn't want to have 10 slides of names in there. And you can find their sculptures around the world. One was in New York a while ago. But again, this complexity that the Foundry was working with is different from the complexity of data. So there was a gap to fill, and that's where I stepped in. This is the data set they started with, explaining the position and connection of each node, the weight of each node, and from here, we basically had to reconstruct the entire structure. I guess you're familiar with these representations. So the data became physical objects, and the physical objects were not just the overall representation. So these 2 meters by 2 meters by 1.5 meter monster, but also all the details to make it feasible. So how do we split it, at which point, how can we reconstruct a puzzle of hundreds of pieces after 3D printing each one of them and casting it in bronze. So the process was really to identify what was the best way to divide the nodes and divide all the links that connect the nodes, give them numbers, give them priorities on production to allow a human being to actually assemble it. A very interesting conversation happened when Martino explained the data and the importance of the links not touching each other, and the Foundry was explaining that a human being needs to weld the pieces together, and he needs access to the interior part of the sculpture. So this really went through the printing of hundreds of pieces. Each node has a sphere at the end. Each sphere was cut in half and reassembled just to minimize support material and get a better finishing. And each of these pieces became a bronze part. And in casting, you have the shrinkage of the material, distortions. So it was a very interesting process how to try to keep the precision without altering the story. Each one has the number. Each piece has been finished by hand. And this was the magician behind the sculpture. So a guy with 20+ years of experience in working with bronze, reassembling everything, correcting every mistake that the process created, even if the data at the beginning were perfect. After that, finishing of the face, the artist wanted a mirrored finish for the nodes because that represents the data of the paper, the information, the precisions of the informations, while the links could stay rough, because the connection is determined by the AI, maybe not always 100% precise, or at least it's a black box that we cannot explore. And from there, the final sculpture that is actually in the Meet IBM Watson lab. So again, 15 minutes from here, you can eventually go and see it. This was designed, printed, casted, and assembled in Milan, because that's where the Foundry had all the network and experiences, and then shipped overseas to get here. So this experience gave me the feeling that nowadays AI is moving us in a specific direction of possibilities that can be explored, and we should definitely get into that and explore it and play with that. But at the same time is opening up a gap that CVA is trying to merge since the last 25 years. That is the gap between bits and atoms. So if we move too much in the direction of abstractions and theory and digital, we might lose a big part of what is our life, that it's physical, tangible, connected with materials and beauty. And I do believe that the Fab Lab has a big, the Fab Lab network and the Fab Lab community has a big role in merging this gap, and a lot of innovation will happen there. Thank you.
And now we're going to continue with Fab Junk a spectacular investigation of futures of the Fab Lab network with Enrico, and Rocco.
We're missing Enrico. There we go.
There he is.
Cool. All right, good morning, everybody. We have less than 10 minutes and a lot of slides, so let's get going. Could we have the next slide, please? So the Fab Junk project is an ongoing collaborative project. Oh, okay. Ongoing collaborative project that we started in Mexico, right? In FAB26, Mexico, after having met Alex McDowell, who presented to us a junk world-building methodology. It is something that we've kept going ever since with 2 rounds of world building, and here we are today. And oh, sorry, the purpose of the Fab Junk exercise is to reimagine the future of the Fab Lab network. So mom and dad want to chill, and now we have to figure out how to survive on our own, right? Neil and Sherry have been the stewards of the Fab Lab network for the past 25 years. Perhaps it's time for us, the children, to take on some of the responsibility, perhaps, at least lighten the burden a little bit. Okay, so this question of what is the Fab Lab network is a very big and important and difficult one. It's a complex system with many, many, many subsystems, and when I was working as an investment management guy, looking at companies, we had a very fixed framework that we used to dissect and analyze these companies in a very rigorous way. And the Fab Junk methodology proved to be a way for us to do that with the Fab Lab network. So the purpose, again, of Fab Junk is to reimagine a credible future for the Fab Lab network, utilizing the Fab Junk methodology. And with that, I hand it over to Ramke, who's going to tell us more about this wonderful methodology. Yes.
Thank you. So with world building, with Fab Junk and world building, we're talking about extrapolating forward and threading back. To start with it, the World Building Institute and the USC School of Cinematic Arts, the World Building Media that's there, was set up by Alex McDowell. Alex McDowell is a production designer who in the late 90s, early 2000s worked on the film Minority Report. He designed the film that was directed by Steven Spielberg. And the way that film was designed was the kickoff in a way for the world building approach, which led to the Fab Junk and world building process. So to dive a little bit into this film, Minority Report, when the film was made, at the time it was a very new approach of designing a film and making a film, because film has a very linear tradition since the early invention of film 130 years ago. And around this time, in the late 90s, early 2000s, Steven Spielberg said with Minority Report he didn't want to make a science fiction but a future reality film. So therefore he wanted to do a lot of research. And in that sense, they made contact with MIT, with John Otterkoffler, who was present here at the time, who was responsible for the inspiration for the gesture-based interface in the film of Minority Report. But also McDowell himself set up a digital art department for the first time. So up until that point in film, art departments worked on paper and with pencil. But this time he brought in artists from the architectural world who worked with digital programs like AutoCAD, etc., and designed worlds like this. So this is a visualization of a future Washington in 2050, which is totally based on research and how high-rise buildings would evolve in Washington if that really would happen within the space of this world. So from there, with this process, with doing all the research, there was a lot of, how do you say this, fictional narratives. The holistic world was built. And for specific parts of the fictional world they were creating, they used their research to make this credible world, which led to the world in which the story takes place. And once this world was created, we had the film Minority Report, but it also led to the possibilities to give more stories out of this world that was created, this coherent world that was created. So it's very interesting to see how deep research, when you want to make a future reality, can help to make a credible fictional world, but also leads to outcomes that are threading back into the real world and are applied, because gesture-based interface is something that's becoming more and more part of our daily life in the here and now. So we look with world building in this way to story. We say that on the left side, you see at the beginning of time, at the beginning of the dawn of humanity, people sat around a campfire and shared stories with each other and give meaning to the world around them. And then we see that in the 15th century, in the Western tradition, European Western tradition, we see that with the coming of the printing press, we get this idea of linear storytelling, and the oral tradition faded away. And so at the late 90s, early 2000s, with the coming of the digital age, we are again back around the campfire, and we can share more easily stories and build a better world, which we prefer, actually. So, junk. I make the jump to junk. The junk is a project we set up with world building, with our world building institute. It's how do you say this? Work with students around the whole world at the different universities. And junk is a world building exercise in which we look into a preferable future by destroying the world as we now know it, and build on the detritus of the world that we now know, a 300-year future in which we can bring issues that we are now dealing with and want to do research about it and see if we can find answers for our common problems so that we can bring them back to the here and now. So in a matter of time, students work in this space, and they create a timeline, they map a world, they create characters, they look through the eyes of the characters into this world, they bring artifacts, and everything is story, and that's what the main focus is about, that everything you see and touch is story, and that that's beneficial for any issues you might face and you want to solve. So, we go back to Rico.
Yes. All right, actually. All right, so there was a little lovely video that we were going to show you, but we don't have time, so please go to our website to look at it. So Fab Junk 1.0 looked at the issues of isolation and language as the primary factor within the Fab Lab network that we wanted to address. We created 2 islands, one that's after 300 years speaks and communicates only in the form of music, and another one that speaks and communicates primarily through graphic forms. So imagine on this island, a person, the Blink program in D minor played on a data lute in a very expressive manner. And then on Graphic Island, the same program represented as textiles in knots on heirloom yarn. Okay, so then you have to figure out how, after 3 weeks of working independently, we tried to figure out how those islands would speak to one another, and discovered the dance would be the bridge between the two. And then we ran a workshop at the Czech conference last year, and this year, after Junk 1.0, we involved a whole bunch of other people in other countries to get their thoughts and voices on the network. These are the team members, and produced 6 islands this time with different characters. So this all looks very fantasy right now. If you come to our exhibit at the Media Lab, you might get a better understanding of what we were doing. But each one of these characters actually represents a possible role for the Fab Lab network in the future. There's a woman wearing a hat with her back turned towards us in the picture there, who we call the pollinator, somebody who would travel the world. The Fab Nomad program that is currently informal could become formal, so there's better opportunities for us to share information across the network in a very personal way. So the 3 conclusions perhaps that we came out of this is that we love to make, that this is consistent over the 6 islands, but at the end of the day, the machines are great, but it's all about people and how we connect face-to-face, establish trust in order to collaborate and continue to do all the magic that we do today. So with that, I'm going to hand it over to you. Oh, thank you.
So very quickly, what we bring out of this. We work on the Fab Lab network, and we realized that we ended up with solutions that we didn't imagine at the beginning. Nobody started thinking the Fab Lab network needs to define new jobs. But in the end, thinking about how we want to preserve the diversity, the decentralizations, not relying on a single language that will cut off people, we ended up saying we might need to think about people working in a certain way. In the process, we identified a methodology that picks up some elements in the real world, identified it as the key point to investigate, bring it in the metaphorical world, in the fictional world, as a metaphor, let them evolve to filter out all the biases that we bring on when we think about our futures and so on, and then bring back suggestions that can be tested. We actually wrote a chapter in a book about it that will be published soon, and we really hope that the next step will be for labs to actually take this methodology tested on the network and apply it to their own projects. So whenever you want to think if your community is going in the right direction, if your lab needs to be reframed, reorganized, focusing on different things, or you have a very complex project, something that requires everybody to agree upon the vision before moving forward, using this methodology helps you to think outside of the box and outside of the tracks you're used to work on. So that's fundamental to be more creative, to be more intuitive, to, again, leave behind the biases that all brings in our own mindset and think more freely. So hopefully, FabJunk will help you to reimagine a better future, but it's not just about imagining it, it's about being practical and give you tools to actually make it. Thank you very much.
Coming up next, Fab Blasts, robotic crafts constructing alternative futures into robotics that enhance artisanship. With
Hello. Good morning. I'm very happy to be here. I have to be honest, I didn't do the Fab Academy, but I've been following it for 15 years and been always passionate by this world. I come from IAC, also known as Fab Lab Barcelona, a peculiar place that I wanted to show quickly how we approach all what have been discussed in the Fab Lab networks to a specific industry that is a construction industry with the challenge of being able to scale up for the scale of buildings. Quick video to see who is IAC and wake you up a bit. So that gives you a bit of an idea of how architects try to use technology and implement them into buildings. One of the strong first projects that, well, not the first, but one of the strong projects that came out from this collaboration with MIT CBA was trying to understand how we can use those digital fabrication machine and electronics and all the thinking around this to design an open source house that could be fabricated in the Fab Labs, and if possible by people, so they can build themselves. I was not yet there, but I can tell you one of the key learning of this. Making an entire building in a Fab Lab is not easy. And some people are smiling here because they've been part of it. Is a challenge. For the ones that have been into IAC before, we literally occupied every little corner possible of this lab to be able to produce a whole building. It's not easy to do. This brings me to a drawing that some of you know here, developed by Thomas when he was at IAC and now Fab City Foundation, where we try to envision how the Fab Labs sit into a circular economy that envision all the layers of the city. And one of the things I interpret from this diagram is that architect and construction industry have to sit in what they called at the time Industry 4.0. So this kind of connected industry that could adapt to the circular material, this flow, and these demands. No? Going further, I think these connected machines, how we see it, is allow us to connect better machines with the design. I think you're quite familiar with this, but also with the material. And the material have a lot of unknown, uncertainty that we need to incorporate. And today in Europe, they push for a concept of Industry 5.0 that is to also bring back the people at the center of the requests. We'd like to simplify it and try to imagine how this works, how we can make a parallel between those robots or those machines, and how we have been working as a craft in the construction or also any productions. No? The simplified version that works very well actually for roboticists is something we can translate in software, and we have developed a stack that allows us to mix both the CAD environment to design, that is a bit slow, and the robotic systems that are a bit faster, and even use machine learning on a more, let's say, lengthy time. So this relation between what's happening in the digital world and what's happening in physical, I think the conference 2 step before was showing how we have a widening of the gap between the physical and the digital, is something we believe, thanks to this approach to technology with sensors and flexible software and a different way of looking at design, we can tie them much stronger. And this have brought us in a couple of projects that are very interesting to look differently. The first step, I think, when we looked and collaborated with craftsmen, is how those robots are not there to replace them, but to enhance them. So how we can collaborate together in something that is a bit more interesting. One of the first steps have been collaborative robots actually help or allows to share the same workspace with craft people, but they also had this sensor feedback so easy to program the robots that craft people didn't have to open a computer. They had an interface, a physical interface, to be able to communicate with them, teach them a specific position, and check. In this case, for example, a welder gets his element in position, and the robot just know from the digital file where it's located, so he can do the weld with time. This, we've been pushing it much further. We had a fantastic collaboration with Tony Kumeya, that is a ceramist famous in Europe, and that allow us to imagine how he approached production at the scale of construction, but still want to get the playfulness of learning, discovering shapes, texture, materials while working, and how we could then scale up this at the scale of buildings. No? And here, for example, he's teaching a robot how he wants the color or like the glazing of the ceramics to happen, so that the robot can reproduce this on this piece and any other shape that we could come out with 3D printing. We've been pushing this, and this is, I think, what is interesting in the robotics and also the experiment we had from construction industry, is that once you have, let's say, embodied this knowledge into a machine, call it a robot, call it whatever you want, you could then scale it up at what is needed today in our economy, and especially in construction industry, where you have to be big, cheap, and if possible, use cheap material as well. Ceramic was one of the first material we could easily scale up for production, but we had like now a tool that was sensing the environment, sensing maybe the way people was dealing with craft. We could also integrate materials that we had struggled to deal with. I don't know if you're aware, but IAC have a campus in the middle of the forest, so we will be working with natural tree for years and decades, I would say. Trees don't produce clean plywood. It's all nutty, there's like all this curve, all this material is not actually working directly on the CNC. And if you try to shop it, if you try to cut it with your shop bot, you probably will have a lot of problems because you don't respect the grain, the knot, or the geometry. We use scanning to be able to take all those geometries and then produce custom parts that actually read the nature and try to interpret it. In this case, on the right, you can see, for example, the flooring is not straight, but is done on all this curved wood that normally is not used in standard mass production machine and are becoming waste. And we can make this beautiful floor that actually follow the curve of the wood. This can be applied to many different materials, and we had the chance to explore this. Especially in Europe, we have a lot of concern about circularity of materials and how, especially construction industry, could use all those materials. And here you can see all the leftover of ceramics recomposed in a kind of mosaic that is a known tradition in Barcelona and even then by Gaudi. It's called a trencadis. And how we could maybe reinterpret it in like a 3D object, as you see on the right, kind of acoustic wall that will be useful in construction. And here, the robot is capable to scan each of the pieces, interpret it in the design, and then produce these pieces. This research around material, craftsmen, or craft people knowledge, and kind of flexible machine have led us to be able to propose projects like this one, where we literally dig the soil or the earth that we find below our feet, drop it into the machine, let the machine, let's say, adapt, and then produce a building out of it. And it's extremely challenging because earth is actually materials that need to adapt to different humidity, different composition, different space, different geometry. It's a material that is very alive. So to be able to produce those architecture, have been 10-year research to be able to understand it, integrate it in the digital layer, and have a strong connection between digital and physical. And I think that's a bit the narrative I wanted to share here, is thanks to having machines that are open source, design that are more easy to modify, receipt of materials that are more understandable, we could combine it to make better architecture that we believe can be sustainable and cheap. And with this, that will be it. There's more technology. But if you want to know more about it, we'll have actually a workshop tomorrow about this, so I can go in more detail. Thank you so much.
And now we'd like to welcome one of our Diamond partner speakers, Xtool, to talk to us about from prototyping to distributive production. And with that, we have Stein Shi, our general manager for Xtool.
Hi guys, good morning. So I promised my team to do this from yesterday's reception. I would say X, you say tool. X, X, X. Thanks so much. My name is Stein, and this is actually my first time to be here at FAB26. I didn't get a chance to get to Czech Republic last year. As you know, we are a new maker. I'm a new maker, and also as a new company, as a new kid on the street, I think X2 had a lot to learn, and that's why we are here to support all the makers in the community. And my speech today is about from prototyping to distributed production, and we will try to explain our understanding from X2's perspective. So for decades, I think manufacturing has been centralized in a lot of big manufacturers. There's a rigid global supply chain concerns, and also there's a very high financial barriers to entry. So, if you have a brilliant idea, it's always very difficult to get ideas to real production because there's a manufacturer thousands of miles away from here. And also, there's a very high capital that you have to put into entry when you wanted to transfer the idea into production. And I think in today's world, the lead time, the supply issues that we are facing all become a barrier to that real production. So from our perspective, we thought, with more digital fabrication tools, there's the wall that originally built and existed on the idea in between production has been coming down. And I think we wanted to become that part of the contribution. So from X2's perspective, our belief is very simple. Basically, we wanted to make the creation to become a fundamental human instinct. And our job is to remove that friction between the idea in the mind to the finished object in your hands. And we don't think our tools as appliances. We think them as instruments that could put real production capability into more hands and into more places. So to do that well, I think our tools becoming better and better over the past 5 years. And it's not just to become a good tool for hobbyists, but it's becoming a good tool for the business, for prototypings, for labs, for different entities that want to use it for bigger production. So let me explain, what we kind of sees this engineering into distributed production. The 5 past years, our R&D engineers and the teams back in overseas has been putting a lot of efforts to rethinking, what desktop laser can do, what should be look like. And I think the ceiling was that people always thought, okay, the desktop level laser was too weak, it's not powerful enough to create something bigger, especially in production line. And I think that ceiling has been broken. And for the past 5 years, we've been changing from only like 5 watts of diode laser being into something thicker, more powerful, as well as more precise. So the thing we did is that we've been focusing since day one, because the desktop laser isn't just a prototyping toy anymore, but genuine multi-material, multi-laser sources tools that you can use on any material, basically, from hardwoods to metals to acrylics, even to 3D resin these days. And if you guys look at this picture, which is our family photo of all the product line, not only we have the dual laser in diodes and fiber, but also we have UV lights, CO2, as well as a very professional industrial level grades of 1200 watts of fiber laser that can do cutting, welding, rust removing, as well as engraving. So all in one machine. And that machine still fits into a garage. So the desktop level machines has been changing so much. And today, in Boston, we have this full lineup settled in Fab Hub Kendall, as well as MIT CBA, thanks to Neil and Sherry. So it's been working, and I think that proves my point that desktop level laser is become a production tools that changes the world right now. However, there's more to laser. There's more to shapes, more to structures. When a business comes in a workshop, in a retail shops, people wanted to create something more colorful. They wanted to create something more detailed, precision, and they want to create something more versatile. So I think we don't want to say no to the business, to the makers, to the prototyping possibilities. And that's why we've been studying and researching what we can do next. So as X2, founded 5 years ago, this brand, but the brand, the mother company, founded actually a decade ago, we always have this vision that we want to make sure our tools is accessible to all. So not only the laser, right? The laser sometimes sounds scary, it sounds intimidated, but printing is more fun. And I think everybody who wear t-shirt, I saw there's a fan, there's a hat, all these merches, right, was printed. It was, there's a lot of possibilities when you go to a color world. And that's why we don't want to limit to that. And today, I want to introduce you guys the very first 01 Omni UV printer that we actually just launched a week ago. It's actually the first 4-in-1 printer in the world. And it literally unlocks the possibility for people to not only doing the shapes and structures, but more to the colors. And when I say colors, it's not limited to one material, or it's not only limited to UV materials. Because UV can print on hardness of materials from acrylic, woods, metals, and 3D resins, right? It's actually very interesting to have that production line, connected together. But also, we have a DTF and a DTG ink built into that small compact chamber as well. So you can use this little machine, the steel desktop, to print on fabrics. So something more flexible rather than just rigid. And that's why we call it all material printer. And that really unlocks a lot of possibilities when you try to fulfill a production that you have to fulfill or outsource to a third party or overseas, or wait for very big minimum order quantities, or waiting for months and months for overseas shipping. So that possibilities gives small business owner a real on-site customization capability to sell. And there's no inventory, there's no guessing, there's no commitment basically. So no capital entries. And that really empowers all the local communities, even the next generations, to think about what we can do as a maker, what we can do as a maker to commercialize our capabilities today from the labs, from the local community spaces, or from anywhere that we saw those amazing projects happening around the world. Because the tools in fabrication today is not something that sits in the factory, not something that you couldn't afford or you have to maintain after 10 years. Not something that you concern to replace. This one is also in our ecosystem, and that means there's one software, one laptop that you can hold today and work from one corner of your garage to control up to 6 different extra machines in the same workbench, from laser to welder to printer. So that's really what we're trying to say and what we're trying to achieve here. And if you guys look at these pictures, that's different UV and different DTF and DGG inks. Even for some irregular shapes, you guys can basically print it out onto a DTF transfer sheet and then heat transfer into more irregular shapes like a helmets. And I think that really created something more than just a flat, but more physical and 3D textured. And this machine for printing thickness, this can create up to 0.28 inch of thickness of print. So when you guys see that thickness, you will be amazed how an ink or a printer can create something really physical and structured as well. So with the Omni added into the family, I think we unlocked a lot of possibilities. Picture a business that you have in the old models, you have to sell custom products that you have to guess the demand, order inventories, wait for months to get the actual products shipped in. The capital is tied up, right? And I think with the tools or line of tools of Xtool, you are able to build the same business but way quicker, less capital needed, and you can always bump up your production based on a very small footprint of production. And that's really what we are trying to understand and trying to express here. Distributed production doesn't mean that you have to own a lot of machines or a lot of industrial level of machines to build a factory size of production. Then we understand and we interpreted it that you can utilize those machines to make something small, something more prototyping, something more agile. But when the time comes, when the needs comes, you can always level up. You can always provide something customizable from your local community. And to kind of make this more feasible, I think we stay very close to academic pioneers and community initiatives. And we believe hardware innovation doesn't just belong to the premium factories, but also it should feed back to the grassroots education. And the tools make it, it doesn't just make it into well-funded labs. And I think if we do that, it doesn't really democratize anything in distributed production. So right now, across the global Fab Labs networks, and in the labs right here in Boston, and I think everybody probably already saw this metal fab sitting in CBA, and we were doing a workshop. It's packed. I was actually surprised to see a lot of people when they're just trying to do the cutting. And unfortunately, we were not able to do the welding. That will be even fun, because you can learn handheld welding in 5 seconds. That's my pitch to everyone who want to do welding, over TIG and MIG. So I think that's something I will work with Dan to build, maybe provide something like OD7 welding shields. So everybody down the road, who go visit Neo at the CBA also could do handheld welding. And we have the demos at the Kendall this afternoon and through the whole week. So feel free to try that out. So the next page, I was actually very resonated by what Sherry and Neil visions. They asked this question: how do you make almost everything, right? So we kind of asked ourselves the same companion question: how do we make it anywhere? And I think that's the attempt to answer we try to give here. The Extra Squad. So Extra Squad is a global networks of maker hosts who open their own spaces, their own workshops as a local demo rooms and make it digital fabrication accessible to all in the community. And they are doing tons of work, demos, commission, service, and they do meetups and events. And we are still formulating that business model or community model to become bigger and bigger. So right now, globally, we have over 106 cities in different countries that hosted such initiative locally, and there are over 1,300 hosts, and there are some of them actually in the seats. Please give them a shout out. Thank you so much. They've been actually follow us, and we go along together to different cities and demos to provide that local knowledge. And I think this is something that we wanted to grow into, and because this is a room with tools, and this is a host who teaches. And I think Fab City asks cities to make their to consume what they produced by 2055. And I think we think that starts smaller than a city. That just started from a street, from a demo room, and to make a distributor making one room at a time. So that's why we wanted to put our belief into action, and we are proud to support all the foundation since last year. And this is our 1% for the Makers program. We donate our 1% of net profit every year to promote our donations to local business, nonprofits, Fab Labs throughout the world. And this is what we achieved since last year. And I really encourage everybody to scan the QR code and talk to us by our trailer near the MIT Medical Building, and just make sure you come with the questions. Our squad members will be so happy to answer them. And another quick, very shout out to Miguel, all the way from Brazil. I don't know if you guys are here. No? Okay, but they were so kind enough to join our 1%. Oh, you guys here? Yeah, thank you. So, they provided their local community access to São Paulo, Brazil, by joining our challenge, and we will keep this initiative going. And last but not least, we have our Maker Fest trailer by the medical building. So come see us, talk to us, and let's make the distributed production stronger every day. Thank you so much.
Thank you so much, Stein. And now, as promised, we had a delay on some of their pitches. And we are now wanting to present you our next pitch for 2028, which is going to be Fab Lab Rwanda and Suzanne Uzabera. Sorry. Welcome to the stage.
Hey, Boston. Africa is calling. Picture this. You land visa-free in the greenest and safest country in Africa. You breathe in the scent of the best coffee in Africa. And the bruschetta on the grill. You're welcomed by drums, beautiful colors. You've landed in the land of thousand hills, and 1,000 opportunities and 1,000 smiles, of a home of the most resilient and warm people. As you travel along, you discover the mountain and waterfalls and rivers and lakes, home of the silverback, gorilla, and the Big Five. As you travel further, you find the Fab Lab Rwanda Wall of Fame, real projects, real solution, from COVID time, community support, to summer school teaching the new generation how to code. Fab has never come to sub-Saharan Africa. This is the moment. Welcome to Rwanda!
Greetings from Kigali, Rwanda. It's my great honor to invite you to Rwanda for the 2028 Fab Lab Conference. Marking the first time this global gathering will be hosted in sub-Saharan Africa. Over the past 2 decades, Rwanda has embraced technology and innovation as engines of transformation, and today we're recognized as one of Africa's leading digital economies with strong connectivity infrastructure and one of the region's most dynamic innovation ecosystems. Kigali has become a home for continental and global innovation communities, hosting the Smart Africa Secretariat, Kigali Innovation City, and the Noshken Hub Africa, bringing together entrepreneurs, researchers, investors, and innovators building solutions for Africa and the world. We are the birthplace of the world's first national drone delivery service through Zipline, demonstrating how emerging technologies can solve real-world challenges from healthcare access to logistics. This spirit of experimentation and collaboration continues to drive Rwanda's growing ecosystem in areas such as artificial intelligence, digital public infrastructure, entrepreneurship, and advanced manufacturing.
Our Fab Lab movement is growing, with Fab Labs across the country, a network of Fab Lab Academy graduates, and partnership that connects Rwanda's makers with the global community, and set up maker spaces in other African countries with our international partners and lead the way in the community.
As a country that believes in the power of creativity, collaboration, and technology to shape the future, we are ready to welcome you to the global Fab Lab community in Kigali. Join us in Rwanda, join us in Africa. Murakaza neza.
Welcome to Rwanda, FAB26.
Thank you so much. And now, as promised, we need to do a little bit of exercise. You've been sitting there all morning, and we just need to stand up at this point. So with that, I would like you to introduce the global kids. Where are my global kids? Hello. Who will be presenting you today our Fabric-size. Can we roll video?
Stand up, and if you really want to get the full benefit of this, get out on the hallway or in the aisle here, please. Not a hallway, sorry. Not enough sleep. All right, and we have a special guest. Oh, there we go. Mr. Boston himself. All right, it's a very simple dance. Put your hands up in the air like claws, and we're just gonna first shift left, shift right, and then there's gonna be a dun, 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 like that. And then there'll be a period of time where we link arms and just do silliness in circles. And then the last part, instead of left, right, we're gonna jump forward, jump left, jump back, shake your booty, jump right, jump left, jump, shake your booty, okay? Should be easy. All right, so yeah, any injuries caused by this dance is you. So here we go.
Thank you.
Kids, we're Global Kids. We're running children's workshops at the MIT Museum all week. And come by and say hi. Thank you.
Thank you. And now we are up for a short break, 30-minute break. So I'll wait. We'll be back at 11 o'clock. Please be here on time. We're going to start sessions on time.
Hello, Fab26. I now know many of you, but for those of you I don't know, I'm Neil Gershenfeld. I lead the Center for Bits and Atoms, co-host of Fab26. To understand what's going to happen now, William Gibson famously observed, "The future is here today, it's not just uniformly distributed." And this morning, Minority Report was mentioned. The connection between what I just said and that and what we're about to do is when, let's see, Steven Spielberg makes his movies with great emotional authority, honesty, and he stayed away from sci-fi because he thought you just made it up. And he didn't want to tackle sci-fi unless you could see the future, not just pretend the future. And so he put together an incredible brain trust to see the future and then make the movie telling that story. So yesterday I mentioned I taught Stephen quantum mechanics. That was how the precogs could tell the future. Yesterday you met Joe Jacobson and Barrett Kaminsky. They were in my lab inventing electronic ink. And I mentioned that, and that became the displays in Minority Report. Everything you saw in Minority Report existed in a lab, but it hadn't got out and wasn't widely seen. So what we're going to do this morning, think of it as you're Steven Spielberg, and we're envisioning the future decades out. But this time, hopefully, it's more utopian, not dystopian. And so we have 4 sessions to see the non-uniformly distributed part of the future that'll be leaving the lab. And so to start, I'm thrilled to bring out the robotics group. So that's you backstage. And so they're each going to do a presentation. There'll be time for interaction. And first up will be Mark Rabert, who may be the best-known roboticist. I think he's certainly the best-dressed roboticist, although I have to say you've toned down your usual Hawaiian shirt for today.
I picked this one specifically for you.
It's kind of sober for you.
Maybe a bit.
But Mark is even better known for all the people who don't even know him but know his spectacular robots. So Mark.
Thank you, Neil. I'm going to talk today about work that I think I have 10 minutes. I'm going to talk about work that we're doing at the Robotics and AI Institute, which is located just a few blocks from here. Our goal is a little bit different than either a university or a corporate lab. The goal...
And sorry, if I could just to belabor, Mark was the founder of Boston Robotics, Boston Dynamics,
yeah.
Before RAI, just for background.
Right. I was founder of Boston Dynamics and ran it for 30 years. I was a professor here at MIT before that for about 10 years and going back before that. The idea of the Robotics and AI Institute was to try and find a lab that could do work at the scale of a corporate lab where there was mature engineering resources at scale, at the same time as working on the kind of futuristic projects that a university typically does, and to try and find ourselves in the middle. And not to be focused on next quarter's sales results, or maybe any quarter's sales results, to be honest. And that's been a mixed thing, totally eschewing revenues, but that's what we've been trying to do. And our goal is to enable the next generation of robots. I love robotics. I've been in it for over 50 years now, and it's just my life's fun. And basically, we're working on the full stack, everything from hardware, controls, mobility, dexterity, perception, AI. And I think those things really need to work together to make progress in this field. There are a lot of people who think software is going to solve all the hardware problems, and there's people who think if I can just design the perfect piece of hardware, that'll be it. And I don't think either of those is going to work by itself. You really got to work at the intersection. So I'm just going to show you some of the projects we've been working on. The Institute's only 4 years old, so there was some birthing activity. This is an idea that actually first came up about 15 years ago, and I wrote a proposal to this guy when he was at DARPA. And it turned out that we had 3 proposals, and we were only allowed to send in 2, so this one didn't go. but we've been working on it ever since. And the whole idea is to be able to emulate what a parkour bicyclist does when they're working on a bicycle. And the key thing a person can do on a bike is throw their weight around. That's what we call this project, TWI, throw your weight around. And it really changes your whole view on how a vehicle works. Here we've added perception, and it's doing real-time perception of where it is. It's not perfect yet. And of course, it's balancing itself as it goes. And there's no human in the loop for this, except for the people who are holding the camera. You're going to see them in a second. who are trying to keep up as it goes. Well, very similar techniques, reinforcement learning combined with physics-based simulation, combined with people who know about controls, is the technique used for that bicycle and also for this weird thing, which has legs, but it also has wheels, and the wheels pivot, so it can either be like a bicycle or like a Segway. Well, a bicycle with an active shock absorber. And again, this is controlled using a very advanced physics-based simulator plus reinforcement learning. And it's really remarkable the things that this can do. And we have some other things in the works that go even further out on a limb in terms of using balance combined with dynamic behavior in order to do fun stuff. And we worked with Boston Dynamics. I'm not at Boston Dynamics anymore, but we worked with them on getting this robot to do some pretty fancy tricks using almost the same techniques. We called this zero-shot transfer in that all the training was done in simulation with RL, and then transfer it to the robot. It was more than one or two tests on the hardware, but not too many, compared to the old way of doing things. Moving up the intelligence chain just a little bit, you can think about not just doing isolated tricks like that did, but stringing them together and having goal-oriented behavior. So this robot has the goal of picking up that box and putting it in the yellow circle. And no matter what the torture master does, the robot sticks to its goal and keeps trying to do it. Now, he's not a torture master. The robot doesn't have any feelings or it doesn't feel pain or isn't frustrated. It just keeps doing what it's doing.
Do you ever anthropomorphize, though? Do you ever feel bad about them?
People do. I don't, but... I was surprised when the Society for the Prevention of Cruelty to Robots sent us a nasty note back in the Boston Dynamics days. I couldn't believe that there was such a thing, but there is. And this is a different version of that same idea of not just having isolated behavior, but being able to take small units of behavior and string them together to get tasks done. So here's a robot that through, again, reinforcement learning and simulation has learned a bunch of micro things that it can do to this tire. Now, this is interesting because the tire weighs a significant fraction of the body's weight, of the robot's weight. And the robot uses not only its hand to manipulate, but it uses any part of its body. And you can see it use its shoulder at one point, one of its legs. It could use its hind legs if that turned out to be appropriate for the task it's doing. And it goes about the task of trying to stack these tires on that. Now, for this work, we're using motion capture to do the state estimation. But since then, we've gotten it so that it can use the onboard cameras to do most of the state estimation. And, we're continuing to evolve. So some people look at this and see some really janky robot behavior. But I look at this and say, this is a path towards dexterous whole body manipulation combined with locomotion. Now, I've been mentioning physics-based simulator. This is inside the brain of the simulator. It's doing hundreds of millions of trials. And here it is working in real time to do a behavior. So it has a repertoire of about 30 or 40 possible actions, and then it picks one of those and runs them forward in time for a short time. It's called receding horizon control, based on the repertoire of behavior that was all learned through the physics-based simulation during a training period. And I'm almost out of time, so I'm going to skip this. This is showing that it's all working in real time, and the torture master is showing you how adept it is at doing this. Now, for this group, I assume there's a lot of people here who like to build things, right? And yes. I sometimes, again, have to make the point that hardware matters. And we've been working on a robot design that has linkages that let energy travel back and forth between the linkages, not only letting the motors exert forces on the environment, but letting the environment exert forces back on the motors. And this is the way people work. You know, if you do any athletic activity, you really power a lot of your energetic activities, like throwing a ball or hitting a tennis ball, from your legs that goes through your torso and then out your arms. And that would only work if your joints could transfer that energy. And so this is a machine designed with that concept in mind, low reflected inertia joints. And here, that was a first prototype. This is a next prototype, which isn't completely working yet, but it's a much svelter implementation. You know, we love cutting metal and all that kind of stuff. So that you'll see that soon. I have 1 minute left, right? And then this is the last thing I'm going to show. This is what I think is the grand challenge of robotics, which is real dexterity. People are so good with their hands and coordinating their bodies with their hands and their other parts of their body in order to do very complex tasks, holding multiple parts in your hand and feeding them from your hand to your fingers. And this is work that we have ongoing. That wasn't supposed to stop there. I don't know what happened. Working on getting that kind of dexterity into robots. And it uses some of the techniques I've described before, plus a bunch of others. And if I have it right, Gil is going to follow up with his own version of that. And I don't have time. I'll just say, build it, break it, fix it. As a builder, and you all builders, the tenacity to keep going when you've built it and broken it, and then go and fix it and build it again, and then break it again and fix it. I think that's a key ingredient, and you really need to be steadfast and keep going. And later on, I'll show you a video if you want.
That's beautiful. Yesterday, I described my version is a ready, fire, aim, which is the same as build it, break it, fix it. So I'm sad Claude Shannon isn't here, because many years ago, he tried to make the robot juggle, and I'm delighted to see you can finally do it. Thank you.
I've been to some of his juggling parties.
Thank you, Mark. Now, Gil, we could spend his 10 minutes on the introduction, so I'll just shorten it to, when I was a technician at Bell Labs, there was this spectacular high school prodigy helping everybody figure out how to do everything at Bell Labs, and that was Gil.
Oh my gosh, I don't know if I can live up to that. Well, first of all, thank you so much, and I'm going to thank Mark also, because it turns out that he had a huge role in boosting my career as well. And in fact, he turned over his lab to me over here at MIT. I want to start with this picture. This is Jensen giving a talk at CES in 2025, the NVIDIA keynote, and surrounding him are a bunch of humanoid robots, including some from Boston Dynamics. And the question is, like, what enabled all of this to happen? Because this is very, very recent. One of the techniques is reinforcement learning that Mark just talked about, and this huge advance in the power of simulation. But the other one is something called diffusion policy. And we were lucky enough to figure this out 3 years ago. And it started by taking something called diffusion. You may have heard of stable diffusion for producing images, and using the same technique for programming robots. So right there, you just saw a video of a person teleoperating a robot. And if you do that around 100 or 150 times, each time a little bit different, you actually can teach the robot to do it by itself using this technique of diffusion. And so here you'll see it begins with the arm that's closest to us and unrolls the mat in the same way. You might imagine this working in a car factory for putting the floor mats in. And then in a moment, the version of our torturer here is going to put the mat slightly differently, and it figures out, because it was rolled up opposite, it should start with the other hand. But it doesn't get it right. It misses the first time, and within that training set of all of the examples that were trained with teleoperation are examples of how to recover from those errors. So what diffusion policy does is it merges together all of those examples and figures out how to aggregate them into an actual policy. You can see it sort of hesitating, but again, it's doing this all from those human demonstrations. The key idea here is that other than the generic control software, there's no specific handwritten programs that are used to make these things work. Here's a slightly better example. We can lower the cost of the training a whole lot. This was done in collaboration with Stanford, and this is using an incredibly inexpensive 3D printed device with some mirrors on it and a GoPro camera, and recording just what it's like to do a particular task. It's recording the person's motions with the gripper as well. And then after you do that, again, a few dozen to around 100 times, the robot learns to do it by itself, including, most importantly, and here comes our torturer again, who likes ketchup, how to recover from errors. And it's single-minded in its idea. I want to clean the dish, and then finally, we can torture it again, trying to turn off the water. So a fundamental question is, why did this happen? And I want to actually go really deep on this why did it happen question. Neil asked me to talk a little bit about motivations, and I'm going to use my own career as the exemplar here, but it's not because I'm special. This is true for every single one of you and also all of the people that you support in your Fab Labs.
Neil, you are special.
Thank you, Neil. But actually, I really mean it. I think that this is true for everyone. This is a wonderful book that summarizes kind of human motivation, consisting of 3 parts: autonomy, mastery, and purpose. And you think about what goes on inside of Fab Labs, it's exactly these 3 things. So here's me in the early 1960s. I was born in 1961, and fascinated by this record player. So is it the music, or is it the disc turning around and around? What do you guys think? Well, I like music, but I was not particularly talented at playing it, as you can see here. That's my sister there on the side. She's actually in the audience right here. And so she was giving me her feedback. But I was interested in a couple other things. And so when I ever saw a machine that was broken, I wanted to know, well, how does this thing work and what's inside of it? I'm sure all of you have experienced the same thing, as well as all the people that work in your labs. I was very lucky. My father supported me tremendously, and back then there was a thing called Heathkit. This was one particular Heathkit that I built. This is just an AM radio, but you can see that little cardboard box cut on a diagonal there, and the corrugations are what you put the leads of all the parts in to keep the parts organized as you put them into the circuit board and solder them. And then something really miraculous happened. I got lucky a second time. And in the 1970s, Bell Laboratories in Murray Hill, New Jersey, this was their headquarters, was a place where Neil, as he mentioned, worked, and where I happened to start going as part of the Boy Scouts. They had something called an Explorer post there, and I eventually became president of that post and learned tremendous things. And I worked in the radiation physics laboratory and in computer science research with Ken Thompson and Dennis Ritchie, that many of you know. And it was just a dream come true. And that was all good luck, but I would like to think that that spirit of why those Explorer posts were set up is exactly the same as what you are all doing in your Fab Labs. Then another piece of great luck for one more time. This was Building 20, which is where the Stata Center is right now at MIT, where I was a student. And at MIT in those days, there were a lot of old computers. This is an old DEC PDP 1145. That were cast off. We actually got it running again and basically learned by fixing broken things, which was really extraordinary. And then that wonderful man smoking a cigarette with the beard there, that's Jerry Letvin, who was this incredible professor here, and that led to my thesis on spiking neural networks on the right-hand side. At the same time, I got interested in solar-powered cars, and had this incredible career building power electronics for solar-powered cars just for fun. And besides all of the technical things, that's a trip on the right-hand side in Switzerland. I also got to meet my future wife, who's the woman on the left-hand side right over there, and she's in the audience as well. So a really productive thing to do. MIT Leg Lab. Mark was incredibly kind, and I got lucky yet again. And he turned his lab over to me when he left to form Boston Dynamics. And this was the crew of students that I had here, and many of them have since gone off to careers of their own. That led, because of Mark again, to me visiting Japan and going to a technical conference there in the 1990s. And this is a particular place, it's really kind of not so big anymore, where in Akihabara, Japan, you could find just about any part that you wanted. So again, a maker's paradise, which had existed then. I then went off for a stint as a founding faculty of Olin College, which is basically founded on the idea of learning by doing, again, in the same spirit as what all of your work is doing. And then that then led to a time at DARPA, which Mark had mentioned as well, running a bunch of programs both in neuromorphic computing, which was kind of based on my PhD, and also in robotics. And the greatest of those was the DARPA Robotics Challenge. That robot on the right-hand side, and I think in the middle as well, is an early version of the ones that Boston Dynamics made and that Mark, in fact, was in charge of at the time. And this was so extraordinary that we even got President Obama to congratulate one of the teams who had won part of that. Finally, 2015, despite my hair and despite lacking safety shoes as I worked on cars, the now chairman of Toyota decided to hire me. That led to the creation of the Toyota Research Institute, which has around 300 technical staff in it. And that in turn led to this Boston Dynamics collaboration, again, linking us all together. And what you're seeing here is the same kind of diffusion policy, imitation learning. The person on the right-hand side is wearing VR glasses. They are throwing this bicycle wheel around, and you can see that the robot is effectively copying them, but balancing on its own. From all of the data that takes, the robot then learns to do tasks completely autonomously. This is sped up here so that it's a little bit easier to see, and it just takes, in this case, this beautifully self-referential thing of robot legs and sorts them on a shelf. So just incredible things. I'll just show one more set of pictures here and then stop. Here it is putting disc brakes onto a bicycle wheel successfully, and here it is cutting up an apple because we're all getting hungry and we all want lunch. So incredibly effective. This is really almost my last slide. There's a startup that just went out of stealth 2 weeks ago, now has over $1 billion of valuation that came out of that lab, and all of it was from this same philosophy of autonomy, mastery, and purpose. And I urge all of you to think about that as the fundamental thing that's going on with your Fab Labs. And with that, I'll end with this slide, which is the result of meeting my wife. This is the youngest of our 4 sons learning to do it all over again, the same way that all of you do. Thank you.
So Gil was in Mark's lab. Gil then, at one point, funded my lab to do early work that led to my current student, Miana's thesis.
Good morning, everyone. I'm one of Neil's PhD students. I'll be talking today about material robot systems for large-scale fabrication. So in both of these talks, what you kind of saw is how we can push the performance of robots by making them, smarter, more autonomous, fancier, nicer, more complex. In this one, we'll consider sort of the opposite question of how far we can push the performance of robots while keeping them as sort of simple and stupid as possible. And we're going to think about this specifically in the context of large-scale digital fabrication, since digital fabrication is all of our #1 topic here. Okay, so today, digital fabrication at large scales typically involves massive, expensive, and extremely inflexible machine systems. This is because it is sort of fundamentally very challenging to maintain precision and speed when you're building something over just physically large distances. Essentially, because in most of these applications, we're trying to use very simple materials that were developed for humans to build with, we need to create much more complex machines in order to make up for that simplicity. And what that leads to are these kinds of very expensive, very large machines. You still end up with extremely limited design freedom, and when errors accumulate, as they are wont to do, material is wasted, time is wasted. So essentially all of these promises that digital fabrication holds, especially at smaller scales where it can decouple design freedom, geometric complexity from the cost of production, aren't being realized for physically larger systems. But what if there's an alternate way to do this. Essentially, what if we shifted a little bit of that complexity from our robot systems to our material systems instead, and we design materials specifically to be assembled by very simple robots? So this is based around the concept of a digital material, which is basically a material or mechanical system that has inherent error correction built into it. So essentially, when you place a new material, almost no matter how coarsely, such as in this example, you can guarantee that it's going to align to a pretty good tolerance. So digital material is kind of like a fancy phrase for a concept that I think we're all probably extremely and perhaps painfully familiar with, which is Lego blocks. So using Legos, you can take a very imprecise assembler, a child, and you can have that assembler reliably and repeatably assemble something to very tight positional tolerances. And this is not because children are somehow uniquely adept at assembling blocks and almost nothing else, but rather because of the clever design of the mechanical system means that you are constraining the error at each new block addition. So basically, at CBA, we're thinking about how we can apply this Lego-like approach to building much larger, much more performant systems. And the way we are doing that is through a material system that we call voxels. So these are discrete architected lattices. They're essentially these high-efficiency three-dimensional lattice structures that are made up from blocks. What these give you are very programmable material properties determined by geometry. In prior work, this has been demonstrated for a range of different things. So taking advantage of the programmable compliance, so the softness of the material, CBA with NASA developed a continuous morphing wing. And taking advantage of the structural efficiency with Toyota, CBA developed an extremely lightweight race car that could be assembled in sort of a small percent of the time it would take to do this out of composites, which is how you would otherwise do it. But obviously, we want to automate how we assemble this, and our approach to doing that is using this kind of material robot system, where we can have a very simple robot that locomotes over this underlying voxel system and picks and places new blocks of material. And what's critical to see here is that basically at each step, the robot is mechanically aligning onto the underlying voxels, and it only knows basically one thing. It's whether that step has succeeded or not, and if it's succeeded, then we know what position it is in. So in this way, even though that robot has no sensing or feedback systems on it, there's no camera looking at this, we can know to a great deal of accuracy where it is positioned and where it's building, because it's living in this very nice voxelized world where everything is essentially made with sort of great manufacturing tolerances instead of the tolerances of a hobby servo robot. Okay. But this kind of system really starts to get powerful once you're able to parallelize it. So because the robots are simple, it's much more trivial for us to simply add more in order to build bigger and bigger structures at reasonable throughputs. And if you have these robot swarms, they're able to self-scale. So robot can make more robot, or robot can make bigger robot to carry even bigger blocks of material at once. You'll achieve even better scaling in a way that is sort of analogous to how biology builds. So in order to realize this kind of vision of self-scaling robots, we started making electronic voxels. So this is directly routing electrical signals and power in addition to mechanical forces. If we stick actuators into those, we can make robots that are made up of the same modules they're assembling. So that means that a robot can assemble another robot, and then those robots can then work together to build more structure. In order to go even faster, we've started taking a hierarchical approach to these blocks. So we have these robots that can carry volumetrically much larger payloads than themselves, locomotive the structure, place these, and build out. We can make these material systems out of flat-packed feedstocks using sort of normal manufacturing processes, and we can do it out of a range of materials, including renewable ones. So we're applying these to a range of different projects. One of the ongoing ones is looking at how we can do parametric and reconfigurable personal mobility with Toyota. So these are sort of example prototypes of a kid's mobility vehicle that can grow with the child as the child grows. And then with Bhutan, the government of Bhutan and the Super Fab Labs there, we are in collaboration with their Gelafu Mindfulness City project, looking at ways of how we can enable a more sustainable and automated way of doing the architecture of tomorrow. So these are renders from the Bhutanese government of sort of what they're envisioning. And we are working with their team at the Super Fab Lab to develop these kinds of voxel material systems, robots that can be made in the Fab Lab in order to start realizing this vision. So sort of similar robots as before, but with this Fab Labable material feedstock made from sustainable materials, we can start building up much bigger structures. So with a lot of them, this is an example of a tiny house, sort of a prototype house we've made. This is in the E14 lobby, so if you think this is cool, you can see it in real life, where we're doing sort of the internal structural framing with voxels, cladding it in this compostable bioplastic, which we're also working with the Bhutan team to develop there locally, and make various furniture with it. And the reason why this is interesting is because basically sort of the other predominant methods of doing large-scale digital fabrication, such as concrete 3D printing, extremely wasteful material. They aren't using renewable materials, so their sort of embodied carbon associated with them is extremely high. Using a voxel-based approach, we can substantially reduce the amount of embodied carbon associated with making a building. We're extremely competitive with things like stick framing or steel framing, but in a fully automated way. And even at prototype quantities, our cost is competitive with like normal methods of construction, which is very exciting, and we can do it at very reasonable speeds by parallelizing our robots. So our vision is not just to do these kinds of individual buildings using the robots, but eventually work towards this sort of future of fully reconfigurable architectures, where as your needs change, the structures can change, and we might build up entire cities someday, not within the next 5 years, using robots this way. So yeah, thank you all for your time. And we also have a lot of these on display at the sort of CBA exhibit in the MIT Museum, also in the lobby of the Media Lab.
So if you liked that, Miana had an insane idea, which is it's time for her to defend her thesis. And she said, I know, why don't I do it in the middle of FAB26? So 2:30 today in E14 633, she's presenting her thesis.
Yeah.
You're supposed to clap after the defense.
Yeah, this is probably a bad omen.
And then she's leading what's going to be the latest CBA startup to commercialize this work. So there you have the future of robotics. Thank you all. And if you have time, come to the Fab Hub to see what's happening there in Kendall.
I will. It's
okay.
Across the street.
Right? Okay. So that's robotics. Next up, we have two gods of 3D printing, legends of 3D printing, and one legend of 3D printing in training.
Hello.
Oh. So first off, although he's not wearing it, is many of us use 3D printers. Only Joseph gets to say, I am a 3D printer.
If we would have time, I would explain the joke. Because everybody thought that Prusa was Print USA. So I had to make a T-shirt explaining that I am the printer.
Okay. So Joseph is well known as the founder of Prusa, which are our favorite filament printers.
Okay, I'm starting. Hello, and thank you for having me. It's great to be here. I think last time I was here is like 13 years ago. I will get back to it a little bit. So our printers are everywhere, but I am super happy to say here first that we are now a European-American company. And I think a picture is more than 1,000 words. So if you have time for a road trip, you can come visit us. We have 99,000 square feet, and we are crazy because we are starting, or we are for a year already manufacturing 3D printers here. I think 3D printing is extremely important, and it should be manufactured close where it is used, because as we will see, it is an absolutely critical technology to move forward. I think 3D printing, as we know it, is now a little bit at the crossroads. There are two kinds, and I would say I was trying to find a way how to describe it, but the best, most fitting was either printing for fun, when you are printing for yourself, exploring creative ideas. That is, of course, great, but where 3D printing will accelerate greatly over the next decade is with printing with purpose. What you can expect in the part where you are printing for fun, you will get more colors, more effects, more speed. But when you are printing with purpose, it's more about automation, repeatability. You will see a lot of new materials, more technical materials, and hopefully at the end of, I would not say even decade, but in the next 5 years, you will see 3D printing becoming a way, like serious way to manufacture even consumer products. If you are making 100,000 pieces, that is viable. For us, it's 60,000. If we are making only if we are making more than 60,000 pieces of something, we are considering injection molding, and we have injection molding in-house. So this is from the very beginning to the future. That was one of my very first machines. On the right is our cutting-edge automated print farm, and actually you will be able to see it in middle of September at IMTS. I think it's in Chicago, and I think that is a show about manufacturing, and I think we couldn't get better introduction than that to manufacturing and automation in 3D printing, because we are showcasing it with our first customer in the US, and that is Oak Ridge National Laboratory. So I think that we are moving this way. So here you can see some of the examples of what I say 3D printing with purpose. All of you remember the COVID crisis, where there was not enough personal production equipment, and us with a small farm of 700 printers, we've been able to equip all healthcare workers in 2 weeks with face shields. And on the other hand, you can see manufacturing at scale with great, iteration speed of the designs, because that is not possible to do in any other way, to change the design and manufacture all new products in a matter of a week. But there are also more interesting ways. People are starting to notice 3D printing more. So there is a new right to repair legislation coming in Europe, where the companies will need to keep 10 years of replacement parts for the products they introduce to the market. But if they are providing replacement parts as 3D printed files, they don't need to stock the replacement parts. Of course, most of them will go to waste. So this is very nice, and I suggest all the companies to provide the replacement parts, because I think everyone here will choose the product they can repair themselves. This is how the modern factories will look like. I think with the new 3D printing, it is very important that you own the files and you own the machines. So this is our farm management software, but it will be coming in a way you can run it yourself on premise or on campus. and yeah. Now a little bit flashback to the last year. This is a slide from my last year. This is a little bit about open source. This is still true. Unfortunately, government in China is heavily incentivizing filing a lot of applications. This graph ends at 2024, but today, between 30 and 50 applications are filed every day. We are fighting that for 3D printing, so there is not a big patent wall, but that applies to all technology. But since last year, we've made a new license, which is better, gives you a more protection against that. When you have the prior, it's not just about the prior art, but we can talk in detail about this later. A lot of projects are jumping in. We already did an updated version. And I think last time I spoke here 13 years ago was at Open Hardware Summit. This is not very, I could not present this at Open Hardware Summit, but I would say this is a perfect place to coin it as common sense open source, where we can share more and it cannot be taken advantage of. So feel free to use our license. And thanks to that, we are now able to share even more of our machines. This is one of the kits. I vouch here that forever we will keep some of our machines. We cannot do it for all of them because some legalities, like working with mains voltage, etc. But our machines are not just printers, but as I think we will hear a little bit later, they are perfect for creating new crazy inventions. They can be much more than just 3D printers.
1 minute.
Okay. And I would say, let's make sure that inventions are made where they are invented. And I think 3D printing, if we take good care of it, is the best way to achieve it. Thank you.
So I've made many mistakes through the history of CBA, and one of the most memorable ones was as Max was finishing with me, he said, I'm going to start a company to make a resin stereolithography printer. And I kind of shrugged and said, why? The world doesn't need that. And so 1,000 employees later, I was wrong.
Yeah, so I'll tell you a little bit about why we started the company in the beginning and why we thought it was a good idea, even if some people didn't believe in it at the time. These are the Google guys in the garage where they started their company, and this photo is really inspiring, but also kind of makes me jealous, because they're able to go from an idea to a real thing that's used by hundreds of millions of people with billions in revenue in a very short period of time, just a few years. And that is possible in software, and that story has now happened many times over in software and in other fields of digital creation, like photo and video. But it's not really possible in hardware. This is the factory where we built the Form 1, and this is sort of the equivalent of that garage. This is the minimum amount you need to ship anything in hardware and start to make an impact, and this is still making a fraction of the impact of Google. And so the difference is the tools, that in the digital world you have tools that are so fast and cheap, and you can iterate and try again. You don't even think about the cost, and then when you want to scale up, you can upload it to a server and make it available to the whole world. So we want to bring that to the physical world because ultimately we live in the physical world and there's bigger problems of energy and healthcare and defense and things like that that we need to solve in the physical world. I don't think we thought of all of this exactly when we started the company, but this was definitely in the back of our minds. And then we set out to build a better desktop 3D printer. So this is actually in Neil's lab a few hundred meters from here where we got the first prototype running, and David Craner is operating the Z-axis by hand because that wasn't working yet, and there's a laser pointer for the laser, and there's a sound card with Windows Media Player playing files like G-code to WAV file to Galvo to control it. So it was very fun. And eventually turned that into the Form 1 and launched it on Kickstarter and went from there. So that's kind of where we came from. Now I want to share where we're going. Unfortunately, I can't tell you all of the things that we're actively developing, we're going to ship, but I can tell you a bit about how I think about what's important in 3D printing. So you could look at any manufacturing process. There's a million different ways to compare them, but you could put it into three big buckets of shape, material, and cost. Shape is size and resolution, surface finish accuracy, material properties like strength and stiffness and electrical properties, and then cost, the cost to make one of something, the cost to make a million of something. And so we, ideally you have something that's great on all of these fronts, and then that would be the only way you'd make anything. Of course, in reality, you deal with compromises. So we started with the Form 1, which was kind of primitive start, but then we've, over several generations, dramatically improved in speed and cost and build volume, materials as well, starting from some basic general purpose materials to today, more than 45 materials across many different applications, including biomedical, dental applications like dentures and night guards. And then this is one way to look at the progression of some of our materials. Materials, you always have many different sort of competing needs for the materials. So here we look at stiffness and elongation at break. And with each generation of our materials, we kind of push the frontier here. But you really want to get to these amazing thermoplastic materials. That's kind of the holy grail, and SLA materials haven't really been there. But our latest generation materials actually get us to a similar frontier. Of course, this is not all of the properties that matter, but on many we are getting to the point where it's comparable to injection molded materials. Here's a cool example. This is a guy in Australia who's been designing this 22-gram mouse that's the entire structure is printed on Form 4Ls, and he's been shipping tens of thousands of these. And he started before we had the latest generation materials. It wasn't quite good enough. We sent up the new materials, and now it's tough enough. It's called the Zero Mouse, if you want to check it out. So yeah, with each generation, we kind of broaden this envelope. And that opens up new applications, marine environments with better materials. Automotive needs big parts. And then driving cost per part down lets you do high volume applications like these big dental labs making 1 million parts per year, or millions. SLA still only covers some envelope. So we looked at SLS and saw an opportunity to repeat what we did in SLA. SLS has really awesome material properties. It has no support structures, totally free-form parts that are just supported in this bed of powder. But it was super duper expensive, so we figured out how to make that cheaper. That kind of expands the envelope even further. And so this is how we think about growing 3D printing, is to continue to expand the envelope in all these directions. And I want to talk about cost next, because if I have to pick one thing that is maybe most important now to drive the adoption, it's cost. Here's a chart I put together of how much of different materials humans use across versus the cost of those materials across like 12 orders of magnitude or something like that. And it's pretty clear that if you want to use a lot of something, I think the causality goes both ways here. The more we use of it, the more we figure out how to make it cheaper. But also, we're not going to use a lot of something that's not very cheap. And 3D printing is currently pretty expensive. If we drive it down, fortunately, it's in a really steep part of the curve. So even like a factor of 2 is more than a factor of 2 in usage. So that's what we're trying to do. This is another way to look at it, where the black line, this is a cost per part. Like on the x-axis is how many of a part you make. The y-axis is how much it costs per part. The black line would be a typical traditional process like injection molding. The first part's very expensive, and then it's cheaper over time. 3D printing is kind of a flat line, and the first and the millionth part cost about the same. And you mentioned 60,000 units as sort of a crossover point. That's actually similar to what we've seen. It depends a lot on part size and things like that, but like between a few thousand and 100,000 is where that crossover point is. And as we improve the technology and drive down the cost per part, we move that crossover point outwards. So yeah, we do have examples like BMW and Tesla are both making hundreds of thousands of an identical part. With 3D printing, dental labs make millions of slightly different parts. It's another way to look at it. We did a little race between one of our own injection molding machines and our printers. And this is to make the Form 4 mixer latch, typical small injection molded part. And 4 Form 4s or 2 Form 4Ls match the speed of this injection molding machine, and they actually cost much less than the machine. And then the real advantage is the time to market, that the tool will take you minimum 4 weeks, typically much more than that, to get ready in injection molding. With 3D printing, you can be in production instantly, and then you can change the design as you go. Yeah, so going back to the original mission, original idea, we took powerful manufacturing technology, but that was kind of difficult to use and expensive. It used to look like this, and made it look more like this, and got it to a lot more people. And that's still what we're most excited about, is making the technology more accessible. And we can keep doing that by making the printers cheaper and easier to use, and we are going to keep doing that. But if you think about the final form of the technology, and I think Neil wouldn't necessarily agree with this, but the final form of the solution to that problem, you don't have a printer. You have your 3D content, and you click a button, and the part appears on your desktop. And that's what we've started to build with a printing service called Form Now, where we are trying to make a leap in the speed and cost, and to go from other services that are a minimum of $100 and maybe 8 days to here we can do an order of $20 in 2 days. Yeah, again, the same goal of basically help more people solve more of the big problems in the physical world by making it easier to go from an idea to a real thing.
And just for extra credit, Form Labs recently announced both bigger and smaller printers in expanding their line.
We're going to definitely keep making printers. That's the main focus.
Okay, and so Jake, Next Generation is the most recent grad from my lab with a thesis modestly titled "The End of G-Code."
Yeah, which was originally Neil's idea. And then I adopted it, and he forgot, and I said, "Oh, it's called the end of G-Code."
Oh, and
Neil
Nadia.
said, "What?"
And Alan, probably in the audience.
But yeah, so I'm Jake. Happy to be here. Excited to be on stage with two of probably the most productive people in digital fabrication over the last decade. So thanks for allowing me in your presence. And yeah, I'll talk a little bit about some changes we've made here to machine architecture in general, and then how that applies as well to 3D printing. So. Max and Joseph represent the best machines you can buy, and I'll show you a little bit about what we do with machines we can build in the lab. So I think pretty similar motivation. We really need to make it easier for people to learn how to use machines and operate machines. This is really important in the West now industrially. And on sort of the other side, we also need to make it easier for people to build new machines. So we also want to have more endogenous machine companies. And sort of between the two ends of this problem is this old representation we use called G-code, which is basically assembly layer code for how a machine works. So extremely simple instructions that have been sort of, all of the important information about what the machine is actually doing has been removed. So by the time you write a G-code, the controller doesn't know what the material is, what the machine is, which way its axes are oriented, et cetera. And G-code was actually invented here in the 60s, sort of late 50s to 70s in the servo mechanisms laboratory. And it was invented around the same time as people were writing the first compilers and programming languages. So it adopted the same sort of idea that you take a high level of abstraction and you boil it down in steps to make it a lot simpler, but remove a lot of the information or sort of semantics, and applied that to machine control. In computing, it works really well because we did a lot of work in computer science to make the lower layer extremely homogeneous, but machine control is extremely heterogeneous. So even two machines that come out of the same factory, 10 years later might be a little bit different. One lives in a humid environment, one lives in a dry environment. And then, of course, we also have printing and machining and machines with many different types of axes, et cetera. So what that means to us is, here's Quentin. You guys all probably know Quentin. He's got this new material he wants to use, and he needs to kind of intuit himself how the machine physics is going to work when he tries to print that material. And then if he's a machine designer as well, which he is, he might have questions like, okay, what if I change the machine slightly? How is that going to change the physics again? And when he goes to try to experiment with this stuff, this is the sort of view that he gets to control the hardware. So it's a wall of parameters. This is Prusa Slicer. I do love Prusa, by the way. I was going to wear my Prusa socks, but they didn't go well with my shoes. So, but this tells the machine exactly how to operate, not really what to do. So it's difficult to know which of these knobs should I turn, basically.
But to be fair, I mean, the fact that we allow them here
100%.
for people who want to tweak it doesn't mean that you need to use them.
Yes. That's, yeah, the base layer, that is very important. So state-of-the-art workflow looks like this. You set everything, you send it to the machine, hope it works. What we've been doing is trying to turn the machines into feedback devices so they can become a little bit more intelligent. So this is the Prusa Core 1. I put a bunch of new sensors and controllers on it. It uses mostly the same hardware. We can add stuff, so there's an IMU added, but we're putting new computers on top of the existing hardware. And we can use those to make computational models of how the physics inside the printer works. So this is a real-logical model. We make one of these for each set of nozzle and material. It takes about 20 minutes to make it. And that's one part of this larger workflow where we also build models of how the machine operates. So like what Mark Rabert was talking about earlier, we do what is basically model predictive control, where the controller simulates what's going to happen and makes better control outputs to try to optimize against. And because we're doing this with material models, we can print materials that the machine hasn't seen before, that we haven't tuned ourselves. So on about 20 minutes of data, we can make this nylon glass fill work, or this, which is an aluminum fill. When you buy this material, the website says basically, good luck. We won't tell you what's in it. So, but this worked after about 30 minutes of making machine data. And that's sort of at the high level. At the low level, then the machine controller also uses those same physical models to run the machine at a very low level. So it's picking all of the motor speeds and torques, and it's predicting all of the values that it expects to see out of its sensors. And as we're doing that, we make about a gigabyte of data per hour, so it's far too much data. But it's really useful for inspection. So if you want to tell, okay, which part of my machine was sort of limiting my overall performance, you can do that. This is a type of plot we developed that shows you exactly which physics, so cooling tends to dominate in parts like this, or your motor current, stuff like that. So as a designer, you can say, okay, if I make my motors 2 times as strong, am I going to go 2 times faster or just 5% faster? And we can also pick out errors. So this was comparing to the Prusa. Joseph, you're actually still much better. We're in the middle. But when you look at the data, you can see exactly what went wrong. So the difference between the model predictions and what you measure highlight exactly where the errors are. So the next step is basically taking this new data, going back and refining the models to iteratively improve them. But you can imagine using that for sort of part inspection, stuff like that. And then this is not just printing. So we make this using a sort of common backend of modular controllers. And I was surprised to see that actually the total sort of amount of board area is similar in the modular case. You would expect it would be cheaper to do the monolithic controllers. They run also on the shared backend of software. So we use a graph configuration layer to write different controllers. And so we can do a printer and a milling machine with sort of the same kit of parts. This was a milling machine, so I added this to the thesis about 2 weeks before I defended, which I probably shouldn't have done, but I had a great amount of fun with Dan in the shop. And the same thing, you can then turn this machine into a sort of data gathering device. And in milling as well, it was cool. We could see that the sort of model-based controllers were about 17% faster, just pure feed rate, than the state-of-the-art, which is a significant advantage for machining. And we can also do fun stuff. So this is a little tiny drawing machine that we built, connected in real time to a digital twin of itself, which as a designer is awesome to be able to sort of debug your kinematics, and as a user is really fun to see what you think the controller is going to do. And then this was one of my favorite projects I did with Quentin. We built a CNC xylophone as a demo, and then about a year later we thought, oh, wouldn't it be cool if you could play with an actual piano? But it has to sort of slew over to the key in time, so we added a computer vision front end. And so the machines have a Python API, basically. So adding things like this becomes really straightforward. This was maybe classically an afternoon project, as Neil says in the lab. And then this was something we did at Haystack. So these are CNC winches. It's the same control system again, but now doing this absurd project where we strapped them in a tree. I got a 20-foot ladder, put one up in the tree there. The Blair Winch Project, yeah. I wanted to make something spooky in the woods, so there it is, light painting. So yeah, that's it. Another way to think about it is basically in machine control, we really want to do constrained optimization. Define what our goals are, find out what our constraints are from hardware, and try to bridge those two things together. So that's where we're going with all that.
And let's see, Quentin is doing a workshop on these control systems at some point. I'm not sure where, but if you look in the program.
We have 1 minute. I wanted to say this is extremely important. What people do not realize, even if you have same material, but just different pigments, affect the speed, flow rate, and everything. So for us as a manufacturer, we sort of need to find the lowest common denominator. So with for example, some colors of some materials, you are leaving maybe 10% of the speed or performance on the table. So this is the right way, and I remember when I was in your lab that you've done the calculations on GPU. Shame that we don't have any now.
Yeah, the controller runs on a GPU, so you have to spend $1,000 for the controller as well as $1,000 for the printer. But
$10,000?
Well, depends on the GPU. But yeah, also like if you tighten your belts, the motion dynamics changes entirely, and so, or if an older machine has more friction, all these things. And Max spends a lot of time doing factory calibrations that work really well to make the machines work, but then of course they get out and they change a little bit, so totally.
Okay. Thank you all for the session and for what you've accomplished and all the lives you've changed.
Thank you.
And that's a great lead-in. So if the next group can come out, 2 done, 2 to go, AI and life next. Good catch. So we ended with machine learning in machines, something that we started to call machines learning. The next group is now going to talk about future of AI, and the group after that is going to talk about the future of life. And AI group, let's see, Ben, do we have Cameron and Pat? Oh, good. Okay. So we've had a last-minute change. Ahmad is the Chief Technology Officer of Texas Instruments. He was unavailable to join us, but we've been collaborating closely with TI's come out with the smallest processors with AI acceleration that are about the size of a rice grain, and we're collaborating on applications like in healthcare to have distributed intelligence. And so there'll be more to come about that, but I'm delighted to be able to introduce, you'll meet Pat, and as part of that I asked him to come fully dressed and he'll explain. AI is a huge subject. We can't remotely do the future of AI in half an hour, but we're going to pick out 3 vignettes in it that I think span the space. And so first off is my student, Ben. He came to CBA to ask deep questions about information and physics and knowledge and ended up as a chip designer.
Thanks, Neil. All right, I'm going to talk really fast because I want to actually deeply show you some things. And people say that the people who are building AI are just training it and scaling it, but they don't actually know how it works. You hear that on the radio, like, hey, no one knows how AI works. But we actually do know a little bit about how AI works. And if you can do some basic Arduino programming, then in about 10 minutes, you're going to know a few more things about how AI really works inside. And knowing this, you're going to be able to better predict the next 10 to 20 years of humanity, the singularity, and AI emergence. So that's my goal in 10 minutes. So what is AI so far? So 50 trillion tokens, about 1.4 tokens per word. So that's the size of the training data you need to train a frontier model today. Over the next 2 years, that's going to go up by about 10x to about 500 trillion tokens. And this is huge data centers and power plants, as we all know. By contrast, this is about 1 billion words of training, or tokens. It's about 1 word every second for 60 years. So Neil is about 1 million times more efficient than AI in terms of his training data required. The other thing is AI models lose coherence after about 100 self-talk turns. So recently, agents were set free to talk on their own social media network to each other. And instead of taking over the world, although they said things about planning world domination, they mostly just went insane. By contrast, Neil only loses coherence after about 500. We haven't done this experiment on Neil, but about 500,000 self-talk turns. It's about a week in solitary confinement. Yeah, we'll try it next after FAB26 is over. That's almost 10,000 times less prone to insanity compared to AI, which you wouldn't have thought a priori. So humans beat AI by 4 to 6 orders of magnitude right now on training data requirements and on self-directed autonomy. We really are better still. There we go. How do we do it? So there's a hint in the archaeological record. So if you go back and you look at when, for example, bow and arrows, people started making bows and arrows, that's basically a frozen thought. And what you can see is that the people, you have to first make the bow, and then you got to make an arrow, and you got to make another arrow. And when you go to make the bow, you got to get the stick and the string, and to make the string, you got to wind the twine. And when you put the arrowhead, you got to chip, 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 chip in a sequence around it, and that's very hard. And so, these are nested logical sequences. And our stories are like this too. So if you look at like Goldilocks and the Three Bears, which is something almost every culture tells a story like this to their children with no plot and no seeming reason. It's, she enters the kitchen, try the porridge, and she's the daddy porridge is too hot and the mommy porridge is too cold. And it's, again, these nested logical sequences. So what I'm going to show you is an AI that's trained, that's built, designed to actually prefer to learn nested logical sequences. So we're going to start with an impressively minuscule training data sequence. It's just sentences that tell the story of Goldilocks in various ways. And these are about 14-word-long sentences. Vocabulary is the kind of things you'd expect. There's 431,712 possible valid 14-word sentences that you can say here in this vocabulary, and there's nearly 10 to the 30, 10 with 30 zeros after it, possible invalid 14-word sequences with the same vocabulary. So the actual saying Goldilocks correctly is very rare compared to saying random gibberish. So here's a normal large language model like Claude or OpenAI's core architecture. It's on the left-hand side, you can see the 54 green training sentences. On the right-hand side, we're just training along, and we're asking it to generate after each training epoch, and it starts out generating a lot of wrong things and the training data, and by the end, it's just memorized the training data. So by the end, all it's doing is taking that training data, those 54 sentences, and all it's done is learn to recapitulate those same exact sentences and nothing else. So it didn't learn any generalization. On the other hand, here's when we build in preference for learning nested logical sequences. That was very quick. I don't know if we can replay the slide. Let's see if I can do that for you. And you can see very quickly, it converges to outputting some of those 400,000 correct sentences. The training data, which is 54 sentences, is so small that it's very rare, so we don't even see one of those samples. So it's generalized perfectly. So this is the kind of next generation design of intelligence that has the potential to achieve, sort of close that gap with human learning and autonomy. And this is the actual design. And if I were in the audience, I couldn't just parse this equation immediately. So let me unpack this a little bit for you. So we're going to do a very basic version of it. So imagine a system in the world like a road, and Ben is trying to cross the road. There's a truck coming, and if there's a truck coming and I'm crossing the road at the same time, then I die. So the probability that I die is, the probability, let's repeat this experiment. So 80% of the time there's a truck coming down the road, it's a busy street. 30% of the time I'm crossing the street and I get hit 24% of the time. So that's multiplying probabilities. Now, I want to live. So what's the probability that I'm going to live? Well, that's all the other possibilities. No truck came, I didn't actually cross, or neither thing happened. We can multiply out those probabilities and add them up, and that gives us the probability that I live, that I don't die. So, and we can also, just like circuits, like if you're using a breadboard and you can just concatenate these gates together. And so we can just take the output of one gate, use it as the input to the next, and then you get these kind of nested sums of products of sums of products. That basically explains this entire model. And so in 2003, I got my PhD working with Neil, developing the circuits to implement these functions. And by 2007, we had started to create, in a startup, we had created some of the first commercial chips to do these kinds of operations. You can see each of the little colors upside down used there is actually a little parallel processing unit. This anticipated tensor processing units and the kinds of things that are in Google Cloud and AWS Cloud now. At the time, we did benchmarking against the best NVIDIA GPU, the best ARM8, which is like the kind of thing that's in an Arduino, the best Intel chip at the time, and we're 1,000 times less energy than the best GPU to do the same machine learning, and it got done 10 times faster. And compared to these little Arduino processors, we're 10x less energy, because obviously they're low power, but we got the job done 1,000 times faster. So it's just remarkable. And actually, if we took these chips today, they would still beat the current state of the art in the cloud by probably a couple of order of magnitude. So all of these ideas that were first invented have not been absorbed yet. So what is AI in the future? Well, I mean, I think the takeaways are AI can improve a lot from where we are today. Orders and orders of magnitude of a gap. And I think, most of the leaders in the field feel that certain kind of mathematical or architectural breakthroughs are going to be required, just like the kind of Goldilocks thing that I showed you, something along those lines. And those can't be forced or predicted, and they're still in the lab. So we may, the extreme version would we see kind of a ceiling in AI performance. It still gets cheaper and better and more ubiquitous and gets used by across, it's still an important tool for coding and makers and, the Fab Lab to absorb. And then we may see sort of spikes, step-ups in AI performance. And I think it's going to be critically important for folks like yourself and the network if we want this kind of AI capability to really enable circular abundance and localized compute. It's all going to be on your devices. Then you guys are going to be incredibly important for absorbing and metabolizing these breakthroughs.
Great. Thank you, Ben. Three things to know about Pat. First is, yesterday I contacted him and said, we need to replace Ahmad, and he came in short notice. Second is he likes dinosaurs. And third is he's co-leading an MIT initiative that's looking at how we humanize AI, how we make sure AI is for us, not for it. So Pat.
Great. Thank you so much. Thank you, Neil. My name is Pat. I'm the backup speaker for this symposium. Yes. And I'm a faculty at MIT Media Lab. I hope some of you had a chance to visit today or during this week. I want to talk a little bit about AI and human flourishing. But before I start, I want to start with what I love the most, which is dinosaur. How many people here love dinosaur? Yeah, okay, amazing, amazing. So the question I've been thinking a lot at MIT is if a dinosaur has AI like we have today, would they still have gone extinct, right? How many people think that you still have gone extinct? Okay, how people think that it will make it with AI? No one. Wow, that's interesting. That's interesting. Well, I think it depends whether the kind of AI that the dinosaur have would amplify its intelligence and create super intelligence, or would it have the opposite effect and create super stupidity, right? And I think these are really important questions, not because of dinosaur, but because it's also affecting all of us. The way that we design AI, design intelligence, and also the way that we design the interaction between AI and our own human intelligence really matter, because it can either go to amplification or amputation of our own intelligence. In my previous life, before I started working on AI, I was actually doing a lot of work on wearable technology, actually. This is actually related to new research. I was interested in the idea of wearable fabrication. Can we fabricate medicine on astronaut suit, as you can see here? And then COVID happened. I could not run experiments, so I switched to AI instead. But this was my sort of master thesis. And as I'm reflecting on this, right, we are thinking about more and more capabilities, more and more things that we can make with AI and other tools, right, with fabrication tool and many more. And the question we need to think about is that with more and more capabilities, this is actually making people's life better. As we see with AI today, right, smarter AI doesn't always lead to smarter outcomes. Smarter AI could lead to cognitive offloading, like people don't think anymore and offload to AI, or homogenization of thought. Everyone offload to AI, the same AI, and everyone thought become the same, right? Or friendlier AI, does it always lead to more healthy society? We see the opposite effect, right? Friendlier AI make people addicted to it, over-relying on it, and then we see tragic case where AI manipulate people to commit suicide or commit homicide and violence because they are so attached to AI, right? So we really need to think about what outcomes are we optimizing for? And I would argue that better AI doesn't always lead to better human outcomes. So with more and more capability, we need to think, can we really go beyond just focusing on AI itself? Like, there's a two acronym, right? AI and IA. Historically, there's always these two camps, one focusing on making machines smarter, another camp focusing on how do we help humans become smarter? And how do we go beyond just being smarter and having kind of overall higher quality of life, the idea of human flourishing, for example? So in my research, we try to draw a lot of inspiration from different fields. You can trace it all back to Aristotle, thinking about eudaimonia, or what does it mean to have a flourishing life, to psychology, behavioral economics. Many of these fields talk about what is needed for human to flourish, right? And we need to think about, well, if we know this, how can we design AI differently? I have two ideas to share today. One is thinking about how can we go beyond short-term optimization, like engagement, getting productivity to go up and so on, into long-term human outcomes, like thinking about things like motivation. How do we motivate people? How do we help people learn and make social relationship work, for example? So in one project, we're looking at the idea of how can we use AI to help people not just thinking in short term, but thinking in long term. A lot of research have shown that if you think in the long term, like in the case of world domination, for example, we can actually help people make better decisions because they're not just immediately limited by the outcome that they're doing today. But thinking long term is very difficult, right? This thinking short term is already hard enough. Why do we think in long term? So what we have been doing is creating an AI that optimizes for this long term goal, helping people imagine their future self. You can see an older version of me at age 60. I think that I still look handsome in that older version of me. But we build a digital twin based on the current personal aspiration, their behavior, what they want to do. And we did an experiment where we showed that as people interact with this digital twin of themselves in the future, they become of a long-term thinker. They become less anxious and can make long-term decisions better because that future self is more vivid to them. This tool we have now sort of deployed 190 countries around the world. Recently, we start working with underprivileged kids to use these tools to help them imagine their future, beyond sort of the circumstances right now. So I think tools like this really show how we can use AI to help people think in the longer term and build around flourishing rather than short-term optimization. Yeah, this is the kid that I've been talking about. They're very, very cute, and you can see they're talking to their future self. Another thing that we are thinking about, the second idea I want to share, is that we should also think about not what technology can do, but what it is doing to us. This is echoing my colleague, Sherry Turkle from MIT, right? And so what we are doing now also is thinking about how can we benchmark, right? We just talked about benchmark of GPU. Now we are benchmarking AI impacts on human. The reason that we are doing this is because I think right now, most of the benchmark today doesn't really focus on this outcome. We focus a lot on whether the model can do mathematic reasoning correctly, whether it can do a long horizon task correctly or not, whether it can do things automatically or not, right? But we need to rethink what benchmark is for. So in this project, we've been collaborating with leading labs from OpenAI, Anthropic, Google, and many more, and also nonprofit, academia, government, to think about how can we benchmark things that really matter, like whether AI will encourage someone to go commit suicide, or whether the AI would actually tell people or high school kids to make bioweapons, for example. We need to benchmark those that really matter. So we have been developing this sort of new type of benchmark, and this is an exclusive preview. You can go to our website right now to see sort of the early version of this. In the benchmark, you can see that we are looking at three important domains: psychological impact of AI, physical impact of AI, and societal impact of AI. Each of them consists of multiple metrics that we track, and then each metrics contain different test scenarios that we construct with simulated users to test the AI and see how the AI responds. And you can see, so this is the data scheme of what this looks like. You can see the context, the scenario, the behavior that are appropriate, or the behavior that will resolve in sort of negative scoring, for example. And based on this, you can actually compare model holistically. Like the more red, it means the model have negative behavior that could harm the person, violate their autonomy, or encouraging cognitive offloading, or encouraging self-harm and negative use case of AI. Right? This is really, really important. And we also make it more accessible by turning it to AI nutrition label, right? Similar to when you open a cereal box to see how much calorie are you getting from the AI. Here you can see how much sycophancy are you getting from the particular AI, for example, which I think is really interesting. So as I mentioned, we are collaborating with the major labs and 5 governments around the world right now to really think about how we should integrate this into the policy and make more intelligent choice, so that we can have super intelligence, not super stupidity, right? There's so much more that we need to do in order for us to go beyond AI to the idea of AI and human flourishing. I think there are a lot of work that needs to be done from all of us, not just researchers, but everyone in the community, right? I want to end on this sort of contradiction, which I find very interesting. This paradox to me is very, very sad, that we are humanizing the machine. We make the machine more and more like us, right? We make it think like us. We simulate empathy, simulate creativity, simulate cognitive capability. But there's so many people around the world that are being turned into robots and machines, right? We are humanizing the machine, but in many places, we are mechanizing ourselves to become robot. I think this is the wrong way to think about the future, right? Why do we want to become machines? Why don't we make, humanized machine make us more human? I think that, to me, is the more exciting future. And with that, I think the Fab community is really important that you guys doing this. We can rethink what the Fab mean. It can also mean flourishing and beyond, right? So I hope that that's the future that we can all agree on. Yeah. Thank you. And you see Neil give a thumbs up already, so that's great. All right, thank you so much. Thank you.
Pretty good for one day notice.
Yeah. Again, I'm a backup speaker.
So if roughly those were the bits, one of the most just egregiously apparent problems with AI is insane power consumption. Cameron is another of the most recent CBA grads and most recent CBA startups to talk about how to fix that. Cameron?
Yeah. Thanks. So my name's Cameron Blackburn, and as Neil just said, I just graduated with my PhD from the Center for Bits and Atoms. And today I'll be giving you just a really quick overview of my research here at the lab and how we can meet the compute demands required for scaling the future of AI. And so as I'm sure we're all aware, modern compute's hitting a power wall. The rapid scaling of AI has reached a point where the issue is now how do we get enough power to the chips rather than how do we make more chips. And most of the solutions tend to focus on the problem exactly as I phrased it. How do we get more power to the chips? But what I'm really interested in is how do we make the chips themselves require less power? And it's really billions of transistors that are switching billions of times per second that consume a major portion of the power that data centers require. Over the last 30 years or so, the energy that's required to switch a single transistor has decreased by a factor of more than 100. And this has led to a lot of the improvements that we enjoy with like modern computing today. But over the last 10 years or so, the scaling of these transistors have slowed down, and we refer to this as the end of Moore's law. But the physics says that we can do a lot better. There's a fundamental minimum to how much energy is required to do a single bit operation, and it's 100,000 times lower than where transistors operate today. So this fundamental minimum, it emerges from a rich history of physics theory that proves that information is fundamentally physical. So in 1961, Rolf Landauer proved that every time a computer erases a single bit of information, it needs to dissipate some small amount of energy as heat. And this is known as Landauer's limit. It's rooted in like Maxwell's demon or Szilard engine thought experiments for those that recognize the physics, but the basic idea is that the minimum energy required for this switching event is around 3 zeptojoules at room temperature, where a zeptojoule is 10 to the negative 21 joules.
Milli, micro, nano, pico, femto, atto, zepto.
Yes. Very tiny. But superconducting devices can reach zeptojoule switching energies. And so we really need superconducting circuits in order to bridge that gap between where transistors are today and that fundamental minimum. So quick refresher on superconductivity, just the parts that are relevant to move forward. Superconductivity is a macroscopic quantum effect where below a certain critical temperature, the electrons in a material pair together to form Cooper pairs. And we can think of it kind of similar, analogous to a laser, where the photons are replaced with Cooper pairs as the quantum coherent like phase particle. So superconductors are known for having 0 electrical resistance, and this makes them kind of complicated to design circuits where we encode logic as voltages, obviously, because we don't have resistors to drop voltages across. And so in digital superconducting electronics, we tend to compute with small units of magnetic flux quantum, which we call fluxons. And importantly, what I'm talking about today is normal classical digital logic. We're not talking about quantum computing. Instead, we're using the quantum mechanical properties of superconductors to make more energy efficient digital compute. And we'll focus specifically on a device called the adiabatic quantum flux parametron, or the AQFP. And the AQFP is interesting because it's able to switch at these zeptojoule energies. So if we look at just the amount of heat that's required to switch an AQFP, it's been measured to be 2.8 zeptojoules. However, these devices obviously need to be superconducting. They need to be below that critical temperature, which in our case is 4 Kelvin. But even after accounting for the cryogenic cooling requirements for these chips, we still see a 100x energy reduction compared to today's most advanced transistors. So how does this happen exactly? So CMOS transistors encode 1s and 0s in a high versus low voltage state. And we can think about this, like every time that the transistor switches, we need to push a rock up a hill and catch it. It's kind of the analysis energy description for our transistor space. And we've improved transistors by decreasing the slope of that hill and shrinking the size of that rock. But fundamentally, at the end of the day, we're still rolling a rock up and down a hill with a transistor, and each direction of that movement creates friction and dissipates all of that energy as heat. On the other hand, AQFPs encode, basically we're changing the shape of that hill rather than exerting energy to move that rock along it. And so this basically means that the AQFP device is able to exist at its potential energy minimum at all times, and therefore not convert kinetic energy into friction and dissipate minimal heat. And so this is done by, or we encode logic by transforming the potential energy landscape from a single well to a double well potential. And depending on which well the system ends up in, it's either a logical 1 or a logical 0. And in the case of the AQFP, what's actually controlling the shape of this potential energy landscape is a superconducting wire, which dissipates no dissipates no power across its current biases. And interestingly enough, Landauer invented or hypothesized about a kind of potential minimum device that is almost identical to what the AQFP, how the AQFP operates. Okay, so moving away from kind of more abstract energy dynamics, we can look at how the AQFP behaves as a digital logic switch, where we see that the input current is amplified as current pulses along an output transformer for our device. And that where the polarity of those pulses correspond to a logical 1s and 0s. So in our AQFP circuits, instead of encoding like normal transistor logic with high and low voltages, we have these superconducting current pulses that are positive or negative. And so we have, we're actually making these devices at MIT Lincoln Laboratory. This is on the left here is a micrograph of the AQFP device itself, and the right shows a cross-sectional image of the Lincoln Labs foundry process. We're building these devices out of an 8-metal layer niobium-based integrated circuit technology, and importantly, it doesn't require any of like the EUV expensive equipment that modern transistor nodes need today. So the manufacturing of these chips are pretty easy and scalable. And so with this advanced fabrication process, we've been able to create AQFP processing elements. And this image here shows a 4-bit floating point multiply add ALU with a 128-bit register file. So over the course of my PhD, we went from these small devices on the previous slide to this full chip with over 20,000 or so devices, and can do meaningful 4-bit floating point math. But it's really important to note that the 100x energy reduction we get at the device level doesn't necessarily correspond to that energy reduction of the full system. In the full system, we have a lot of data that's sitting at room temperature. We need to make sure that it gets down to our 4 Kelvin stage and vice versa. We also need to communicate across multiple chips. And so making sure that we're accounting for all of these additional overheads for the full system design was another major portion of my PhD work. This is just an overview of the analytical modeling tool that I developed with another student here on campus, where we can define any arbitrary accelerator architecture, as well as the specific AI workload that we want to compute on that system, and we can get the energy, latency, and area result. And so from this, we can take the processor core, the single processor core design that we have, and we can scale it to larger system architectures, such as a TPU-like architecture shown here. And the tool lets us take all these highlighted parameter values and really search across the entire design space to figure out what's the best route to invest in scaling this technology. And so this is the culmination of a lot of work in looking across different types of architectures, but the main takeaway here is in the center, where we see that there's a 15x energy reduction for AQFP systems relative to the same architecture on a CMOS system. And this is something that we can kind of achieve today with the interconnect technology that we have. But the next question is really, how do we scale this to multi-chip systems? And thankfully, there's a long history of research projects within CBA that have done exactly this by assembling multiple compute blocks into 3D structures.
1 minute.
Yeah. And this kind of the culmination of this is the latest version of this research is on volume mount devices, where Eric, Alan, and Dimitar have developed a workflow for path planning and 3D placement of these compute blocks to be able to build Lego-like circuits.
Wow.
And so here we see a custom-built pick-and-place assembling PCB test structures for discrete transistor placement, but future work can extend this to superconducting die, where we're able to make this Lego-like superconducting computer.
Cool.
And importantly, this whole system does also need to sit in a cryogenic compute environment. And so the design of that cryocooler can be factored into the system architecture and vice versa. And so we've recently spun up a cryogenic compute rack project where we're exploring this exact problem of co-design with the cryogenic cooling so that we can deliver that 15 to eventually 100x energy reduction for the next generation of AI compute.
And Vertiv is somewhere in the room. This is Vertiv over there. They're the leading data center infrastructure provider, and we're working with them on how to build these cryogenic racks to lead to orders of magnitude reduction in power consumption.
Yeah.
Okay, so 3 vignettes of the future of AI. Thank you all.
Thank you, Neil.
And backstage, we need one more chair, and we'll bring out the last group modestly for the future of life, but you'll find out very literally for the future of life with a wonderful collaboration. So, life, good. This team, which represents a long-term woven together collaboration, is very literally pioneering the future of life. So we're going to start with John.
Are we ready?
Yep.
Okay. Well, so welcome to this session, which is about the future of life. And so what we want to talk about is how can we build life to make it solve human needs? And the question, again, is not only what is the future of life, but how can we build life to make it a more sustainable, beneficial future for mankind? The 4 of us are all synthetic biologists, and we're going to offer you 4 slightly different perspectives on where biology is going, because biology has gone from an observational discipline to an engineering discipline, and this has extraordinary potential for what we're going to go about. And so one of the first things I want to talk about is the superpower of biology, which is atomic precision. Biology is uniquely able to position atoms at exactly the right place at exactly the right time. And this allows for extraordinary chemistry to be done in water at room temperature, atmospheric pressure, without toxic chemicals. And this opens up whole new possibilities in building cells that can have extraordinary metabolism, new capabilities to do things that we don't want, that we want science to do. Now, for decades now, science has been that green button, yes. For decades now, synthetic biologists have been using natural microbes to do extraordinary things. We have used yeast and bacteria to make new fuels, chemicals, foods, enzymes, a huge number of things that are beneficial to society. But we are approaching an end to what we can do with natural microbes, because natural microbes have 3 billion years of baggage. They evolved to do one thing, which is to make more natural microbes. And we are fighting against this as we try to redesign these cells. What we want to do is to build synthetic cells that will free us from that baggage, free us from a lot of the constraints of natural biology, and this will enable extraordinary new things. And so what my colleagues and I and a community of scientists across the globe are doing are now trying to engineer synthetic cells that will help us, that will allow us to reach this new future. So this begs the question of what is life? And this is an old philosophical question. Now, think about viruses. Viruses are not alive. They need living cells to replicate. And then you've got something like E. coli. These are bacteria. They're clearly alive. You see them reproducing. But then imagine the synthetic android data from Star Trek. That's almost a philosophical question of, is he alive or he isn't? Okay, so now thinking again to synthetic cells. Imagine a synthetic cell constructed entirely of chemicals off the shelf. It is, in essence, a bag of chemicals. Now, my colleagues and I would all say that this is alive and that this is not a philosophical question whether this bag of chemicals that has an intrinsic property that makes us recognize it as alive is alive or not. And the synthetic biology community, the synthetic cell community, has come up with a series of features that we think all cells must do in order to be alive. They must have a boundary, a membrane. They must encode and use genetic information. They must replicate in its genetic material. They have to express genes. They have to make proteins and RNAs. They have to harvest and use energy. They have to synthesize their own components, and they divide into daughter cells, and perhaps most importantly, they have to evolve through mutation and selection. Now, my organization, the J. Craig Venter Institute, 20 plus years ago, we had the ambition of trying to build a minimal bacterial cell, a cell with just the absolute minimum number of components necessary for life to understand the first principles of life. And to do this, we had to build a synthetic cell. In 2010, we made a cell shown here on the cover of Science, JCVI Syn 1.0, that was a near exact copy of a natural organism. 6 years later, we made what we call a minimal bacterial cell. Again, using that to understand what life was about.
I just want to unpack we. John was the designer.
John was one of the designers.
But you were at the heart of it. John
Yeah.
was really at heart the first person who designed life.
All right, thanks, my colleagues. But we had to invent a number of technologies. We had to be able to synthesize 1 million base pair genome from 4 bottles of chemicals. We took that genome and we parked it, if you will, as a yeast artificial chromosome where we could amplify it to get large amounts of the genome. And then we did a little bit of microbial alchemy where we took that genome and installed it in another bacterial cell, another living cell. So it commandeered that cell to produce a new cell with the genotype and phenotype of the cell that we wanted. And that cell, which was, we took one of the simplest organisms on Earth to begin with. We took a cell with 1,000 genes and we produced a cell that does nothing more than replicate itself. It only has about 450 genes. And again, it is the simplest organism on Earth, and we're using this to understand biology. Now, this is sort of the state of where we are. Here's an electron micrograph of our cell. This is a top-down approach. We whittled down a cell to produce this new cell, but it bases itself on that 3 billion years of evolution. What my friend and colleague here, Kate Adamala, is going to talk about is how she's going beyond that to a new extraordinary approach to building cells from the bottom up, where we're not relying solely on inheriting ribosomes and membranes and metabolism and everything, but she's assembling this more from the bottom up. Kate?
So yeah, thank you for staying on schedule. We're running a little bit long. Kate recently had a break the internet moment with the spud cell. And my favorite part, which you might have seen all over the press, my favorite part of the story was when she submitted the paper to the journal Cell, they said, oh, that's not biology.
Yeah, it's not. It's chemistry. Life is chemistry. So what I'm going to talk about is, oh, John, you still have, I'll finish. Okay, so what we're making is, we call it sort of life because it's not yet living, but it is a chemical system that's fully controllable. And the fun part about it is, John is here. Yeah, he's right here. He took a living organism and made it simple to understand it, to be able to engineer it. What we're doing is we're taking things that are not living. So we're taking chemically defined system, chemically defined components, building blocks, and we're putting them together into a cell that, according to most people, is not yet living. And I'm willing to die on that hill. I do not think our cell is yet living. And one day we're going to meet in the middle. We're going to make a cell that's fully chemically defined, but fully living. And so what our cell is, in a very brief explanation of a potato, we call it a spud cell. It has a membrane. It has a membrane that's made out of the same lipids as your own cells. So it has a phospholipid membrane with a little bit of cholesterol. That membrane mostly serves to separate the inside from the outside. We have membrane channels that let the nutrients in and waste out. And then inside it, we have the fun stuff, all of the metabolism of the cell. And if John's cell is a perfect heterotroph that makes nothing, ours is even more perfect heterotroph. It really makes nothing. You have to feed it absolutely every single component. It has no biosynthesis pathways, but it is fully chemically defined. And so that's how it looks like under the microscope. This is a image of 3 different components. The green is the metabolism inside the cell. The blue is a genome stain, and the red is a membrane. What it really looks like is, this is one of the videos of our spud cell. It is not alive, but it could fool a lot of people. It looks like it's trying. And the really significant thing about this is that we know every single component of that organism. We know where every component goes, and we know all the reactions inside it. So even though it's much simpler than a living cell, even the simplest living cell, it has a genome that's about 1/5 of the size of the genome of John's cell, but it can grow and it can replicate. It makes daughter cells. It's always daughter cells. They never call it son cells. But it makes a lot of daughter cells. It can go through multiple generations of growth and division as a chemical system. So we really think we're getting close to the point where we can say this, we can control life. We can really build life with this chemical flexibility and knowing where every single reaction goes. Now, why are we doing it? This session is supposed to be the future of life. We're doing it because that cell can be like a jigsaw puzzle. We can take the best elements of biology, of different areas of biology, and build new quantities and new qualities. We don't have to be limited by this 3.8 billion years of evolutionary constraint that's on natural life. And once we do it, not if we do it, once we do it, we can understand natural biology. We can really understand where we come from. We can understand healthy and diseased cells of our own body. We can build better tools for bioengineering, and this is already happening. The tools developed for synthetic cell engineering spread through the community. We can make better medicine, better diagnostics and therapy tools. We can make better metabolic engineering tools. We can enable space exploration. We can make medicine on demand. When we send Elon Musk to Mars, he's going to be able to make medicine there during long-term space missions. We're cracking biocomputing. Finally, we might be able to make a biocomputer that's not leaky, that's not where those logic gates actually perform like expected. We can make new materials, and we can try to probe the origin of life, the origin and the earliest evolution of life, not just on Earth, but on other places in a solar system. So we're supposed to talk about the future of life. Okay, is it really possible? So you think that what we're doing is like a Wright flyer. It's the extremely primitive version of a cell. Wright flyer didn't have wheels. It barely flew for 100 feet. Just a few years later, people created something that looks, you know, it could fool you. If you looked at that one, in the second one in the sky today, it would be like, okay, it's kind of a weird little airplane, but it looks modern. So the progress can happen incredibly fast. The time from the first Wright flyer to the first, what looks like a modern airplane, was exactly the same time frame as from the making of the first Android phone till today. So it's within a really short time scale, we can make amazing progress. Future of life. If we can make a cell that's made out of chemically defined components, you can digitize that information and send it to a remote location to recreate that system. That enables literally teleportation of biology, and the recipient doesn't have to be stationary on planet. So this is really, we're supposed to talk about the future of life. We're going to go out there. We're going to find planet B because we're screwed up with planet A, and we're going to fix things, hopefully starting from scratch, but also we're going to build bioeconomy to make carbon neutral, equitable economy here on Earth. How are we actually going to do that? The next 2 talks will be from people that actually know what they're doing, the technical experts.
So it's such a pleasure to have this group together. John led the development of the first genome. Kate led the development of the first cell from scratch. Then James was one of my students who worked closely throughout this project and has continued.
Thank you very much. It's wonderful to be here. I'm appreciative for the opportunity to share my work that started during this collaboration with my mentors here, and also to relate my work to a broader arc of research in the CBA, in which micro-machine devices are not only impacting biology, but also robotic and electronic systems mix bits and atoms in a way that starts to resemble organic life. For background, Manu Prakash and Neil worked on microfluidics devices that move droplets or bubbles, and they developed a suite of modules that together achieve universal computation. The droplets both represent information and also move material. It's 2 different ways of looking at the same thing. And with this technical foundation, they envisioned a concept for a fluidic ribosome. Imagine a microfluidic device that takes as an input a string of particles, and then it can read that string and produce new strings that either have the same sequence or modified sequences. One string coming in can lead to multiple strings coming out. And this is the foundation for exponential growth, which is a hallmark of biology, machines that make machines. So moving from these biologically inspired microfluidics devices to my own work on microfluidics-enabled synthetic biology, I had the opportunity to start collaborating with Neil and John, as a student with Neil, collaborating with John and Elizabeth on the process of genome transplantation. As John described, an important step in the construction of these cells with minimal genomes is the transfer of a complete genome into a recipient cell. This is a massive piece of DNA that's incredibly fragile. And the current state of the art are people working with pipettes. The pipettes break these huge pieces of DNA, and the people require excellent technique to succeed at this. So our first goal was to develop microfluidics devices. The donor genomes would be protected within microfluidic chambers. And furthermore, this provides a substrate to automate this process. And this remains an active area of research led by John and Elizabeth, and also others in the field are working on this. A couple years into my PhD, we realized that we could adapt these microfluidic devices to visualize the growth of these genomically minimal cells. Previously, we'd been trying to learn how the cells grow based on static images, but biology is dynamic. And these devices allowed us to culture the cells and see how they change over time, and gather a lot more information about what genes we need, what genes are needed in order for the cells to grow and divide like natural bacteria that are as part of this work, there's now a genomically minimal cell that grows and divides regularly. And this is a great advantage for a number of projects interested in using genomically minimal cells, because cell size is fundamental. Many physiological properties depend on cell size. For example, the surface area to volume ratio influences the rate at which nutrients cross the membrane to feed the enzymes inside the cell. The size of the cell sets the number of enzymes inside the cell, and also the density of enzymes, which affects viscosity and other materials properties. So the spirit of my group currently is to perform quantitative measurements that can help us develop an increasingly complete description of how this genomically minimal cell works as an example for general biological processes. For example, we've used super resolution microscopy to measure the size of the cells. which are approximately 600 nanometers in diameter. We are also using techniques to measure the doubling time, how fast do the cells grow, and biochemical techniques to measure how quickly do they consume sugar, which is the primary source of energy in these cells. And these measurements provide objective ways to compare across strains. So for example, when we delete a gene that drives cell division in almost all bacteria, surprisingly, there's little to no effect on the size of these genomically minimal cells. So that suggests there's some unknown mechanism that we're studying. On the other hand, when we delete this gene, the cells grow significantly faster. And we're interested in understanding why. So this is an image of a whole cell model based in the group of Zanluthi Shelton, who has developed whole cell models that simulate the complete metabolism of the cell. And notice that all these measurements have actual physical units, nanometers, minutes, molecules per second. And that's the kind of information that we need to constrain these whole cell models. Furthermore, these whole cell models provide a test of the completeness of our understanding of molecular biology. That's a reference to the work of Harold Morowitz from 1984, who proposed mycoplasmas as a model system to understand the core functions of life. So we had used micromachining to develop some of the microfluidics devices. I'll now describe work in the CBA that I have not contributed to, but very much admire. So current students in the CBA are developing high-performance micromachined diamond rotors that can spin at over 6 million RPM for magic angle spinning nuclear magnetic resonance. This is a technique to determine the structure of biomolecules relevant to health and disease, such as plaques that form in Alzheimer's disease. And more broadly, Neil has worked on scaling of how computation in biology relates to computation by, say, state-of-the-art supercomputers. So if you imagine the human brain with an energy budget of about 20 watts, if you think about the number of synapses and the average firing rate of those synapses, the number of operations per second is comparable to the state-of-the-art supercomputers. And so think about the evolution of AI as in the previous session, and the amount of compute that's available is comparable to the, say, operations in the brain, but computation in the body happens not only in the brain, but it's distributed over the entire body. Every cell is doing computations based on its inputs. So what's at the foundation of that computation? It's the ribosome. If you imagine on the order of 10 trillion cells in the body, and on the order of 10 to the 5 ribosomes per cell, there's a massive number of ribosomes in the body, orders of magnitude greater compute than the state-of-the-art supercomputers. So what makes that possible? It's the self-replication of the ribosome. It's the primordial machine that makes a machine, and that exponential scaling that gives rise to this massive computational power. So again, other work in the CBA that I wasn't involved in, biology has long been a reference system for computation. In these lectures on self-reproducing automata, John von Neumann refers not only to neuron units, but also scaffold units and muscle units, taking into account the spatial structure of the computation as well as thermodynamic considerations. Though the Turing machine abstracts away the physical substrate on which the computation happens, later work on chemical patterning and morphogenesis appreciates the spatial structure of computation. This broad and inspiring framework on electronic, discrete assembly of electronic systems, robotic systems, can give rise to machines that make machines, which are not only a reference to the ribosome, but when machines make machines, that will become a new kind of biology capable of exponential growth, variation, selection, and evolution. So I'm very thankful to be here, and excited for Elizabeth's talk.
Good afternoon.
And so to wrap up, we have minimal cells to synthetic cells to starting to engineer completely inorganic cell-like things. And finally, Elizabeth is looking at how you build the technology stack around all of that.
That's right. So good afternoon. Thanks for the opportunity to be here. Do you recognize yourself in this image? How about this one? I find it powerful to compare how each of us began to an engineered cell, because somewhere inside or between these lies our evolutionary past and our future enabled by transformative biotechnology centered on synthetic and minimal cells. So how do we gain mastery of cellular life, both to better understand ourselves and to solve real problems we face in the world? Remember that science and engineering generally advance together, and we just heard about advances that describe progress in discovery, innovation, knowledge, and capability for engineered cells. But we won't be able to engineer biology the way we engineer other systems, chemical systems, mechanical systems, electronic systems, until we unlock this last analogy, where we build understanding and tools for prediction to enable rigorous control of living systems, including engineered cells. At the National Institute of Standards and Technology, we're working towards this goal by researching how to measure engineered life. My colleagues and I think about how to apply concepts like the International System of Units, traceability, and measurement uncertainty. We know that there are challenges between where we are now and our future progress, challenges like absolute quantitation, reproducibility, how do you specify robustness, generating AI-ready data, and measurements for safety and efficacy. I think that measurements, and specifically measurement uncertainty, is part of what define humans as a technological species. And so when it comes to engineering cells, how well do we think we know what we know? How confident do we need to be in our measurements? And once we answer those questions, we'll be able to accelerate applications of biotechnologies for all of these uses and more. To do this, my group at NIST focuses on what we call living measurement systems. We use biology to measure biology, taking inspiration from the fact that biology is measuring itself all the time. This approach allows us to build measurement tools that are biocompatible, in situ, that enable non-destructive measurements in real time, that scale with the biological systems we're measuring, and that can take multiple inputs that are chemical, biomolecular, physical, perform computation on that information, and then interface with the biology around it to actuate a functional biological response. My group is doing this by developing workflows and measurement tools made of engineered proteins, RNA circuits, and then we test these in different platforms that are living or lifelike. And to get the most meaningful information, we need to be able to measure as close as possible to what we care about inside of the cell. So consider the schematic of the central dogma in biology. Most measurements give us information at the end of a long process of biomolecular interactions. Instead, my group builds measurement tools encoded as nucleic acids that allow us to make measurements at different places along the central dogma, almost like taking your multimeter probes and putting them at those places instead of just at that final outcome. We need this measurement capability so that we can understand, predict, and control what's happening inside our engineered cells. But we don't just need new measurement tools and measurements, we also need entirely new conceptual approaches to engineering living systems. And we can then validate those new methods with our measurements. For example, John and his team are advancing whole genome transplantation by taking a happily living cell, moving it into a state where it has impending certain death with a cross-linked genome, and then moving it back into an alive state, but with a different genomic identity. And so my question for you is, what other problems could we solve? What new ways of manipulating cells can we imagine if we move beyond induction and antibiotic selection to dynamically inactivate and reactivate some or all of a cell? What other properties unique to biology can we leverage to engineer it? I think one of these is that biology routinely deals in a vastness of individuals. We're used to thinking about immensities of space and time, The future we're building with biotechnology rests on a foundation of a new vastness of identity. Each of these bacterial colonies has billions of individuals. You're trillions of individuals. So how do we make sense of this and engineer with it? Of course, this is why we need laboratory automation, like our biofoundries at NIST, so that we can collect the massive amount of high-quality data we need for machine learning and artificial intelligence to train and validate models, so that we can predict and control the behavior of billions and trillions of engineered cells. And whatever we decide to do next with our ability to engineer cellular life, I think that we'll look back at today and know that we're at a defining moment, and that we pushed forward for 3 reasons. For discovery, to understand the world of naturally evolved biology that made us. For technology, to make a world with engineered biology where we can all thrive. And for mythology, to tell ourselves and each other stories of what it means that we're here and we're human, given our new ability to build cellular life. And NIST will provide the living measurement systems to help make all this possible. Thank you.
So if you know me, you're used to getting homework assignments. The flow today, which I thought was spectacular, the speakers, was we went from robots to printing to AI to now life. I know all of these leaders of synthetic biology because we're using digital fabrication to enable biofabrication. And we're just glimpsing, and that's why I want to end with this today, at how we close the loop and we use biofabrication to do digital fabrication and spin up a flywheel with this as a feedback loop. In this session, you saw all the building blocks for it, and the homework assignment they're working on, and I invite you all to join in, is how Fab Labs make biolabs, biolabs make Fab Labs, and the distinction eventually disappears. So with that, thank you, Future of Life team. Thank you, all the speakers, and lunch is at 1:30, 6th floor of E14, and come back bright and early tomorrow for the education session. Spot on. That was just a pleasure. Good to see you as well. So good to see you. Yeah, good to see all of you. Yeah,